right, welcome to day 2 of the workshop. Nice and chilly this morning. So in this session, we're going to be talking about our vision for an open cloud. I'm John Stumpf, and I recently joined the MOC Alliance to help drive industry partnerships and collaboration. I was recently with 2 Sigma, where I ran infrastructure globally. Prior to that, I did the same thing at Johnson & Johnson, Moody's Corporation. Infrastructure has been pretty much a part of my life for the last 2 decades. And in this talk, I'm going to present our vision for an open cloud. So what are clouds today? You know, they're large, they're monolithic providers of services. They're very capable, but they're in it to make money, lots of money. You know, they maximize revenue, they reduce expenses, and focus on those services that service the majority of the market. So it's difficult for small, innovative companies to break into that market. And there are also examples of the provider, these cloud providers, competing with the technology providers that are trying to break in, particularly on the software side. And these environments are almost always all virtual, and so it's hard to optimize to the bare metal, you know, looking below that virtualization layer. So what do we mean by an open cloud? There are similarities to a commercial cloud. However, in an open cloud, we want to foster competition between the technology providers at all levels, so bare metal and up. The MOC Alliance will be an enabler, not a competitor to the providers, and our focus is on research and academia. Now, the MOC has been developing a vision for an open cloud to enable different groups to stand up cloud services in a level playing field, and where the services can grow and shrink on demand, no different than the commercial clouds. But we want system researchers and developers to be able to discover new issues and develop new services and have multiple data centers participate in this overall cloud, this open cloud. These capabilities are increasingly important as we look forward to expanding the MOC to address the needs of the AI Alliance and the National Artificial Intelligence Research resource there. Now, the MOC will provide the cloud under one operational model. Will enable providers to deliver the services and capabilities on which they want to conduct research and serve the broader community. The providers will deliver specific capabilities as they choose, where they choose, and the providers do not have to deliver the same capabilities in every location. It's where the market demand and where they feel that they can get the most benefit for themselves. It's not a free service, and the technologies don't have to be open source. We encourage you to, but they don't have to be. So we believe robust competition at all layers maximizes innovation. And the MOC Alliance can provide real data from real users of the technologies at scale. This is unique for this kind of environment. So how does all this work? Multiple entities stand up racks of computers in our facilities, and then computers that can be easily shifted between these workloads, are allocated to various services that are delivered as infrastructure as a service. And then higher order services are built on top, and users consume those services at any layer across the multiple data centers. And our vision is that the cloud services can be operated by a common team across those multiple data centers, where if a user asks, say, for NERC, they will specify a location, and if there's enough demand, a service can be stood up in another data center on the hardware there. Now, this is all real today. And in the talks that you're going to hear later in this session, we're going to be introducing the technologies that we use to make this happen. We have over 1,000 computers in the MGH-BCC that are controlled by technology and delivered via ESI. This is one of the technologies that allocates and provisions the physical resources so that we can build on top the services. And we have 4 production services on top of this. We have the Open Cloud Test Bed. It's a national cloud test bed for system research. We have the NERC. Scott and Wayne are operating at the OpenStack VM service and also operating an OpenShift container service. And then there's volume and object storage that are serving 150 petabytes of storage. Now we're really excited that we already have a higher level services running and being deployed. They're all covered yesterday, and OpenShift AI is an AI as a service offering, and we want to have more involvement on this platform, and we're hoping to draw the AI Alliance to this. Chris was talked about earlier yesterday, and the core business services to enable all of this is what the MOC Alliance is going to provide. Things like user authentication, self-service allocation, and invoicing. This is one of the key things that was delivered recently, that we can actually bill back for those services that are being used. We have about 800 students in 3 courses that are using the platform every day, and many researchers. Now we're very excited that Lenovo actually is one of our first providers in this new business paradigm where they're delivering hardware. We're not buying it. They're delivering hardware and they're charging it based on a consumption model. So they charge the MOC Alliance, and then as our researchers are using that equipment, we will then bill them to recover those costs. There are 64 NVIDIA GPUs in this particular stack in this one transaction. It demonstrates the idea of where we can have this level playing field at all levels. So even at the bare metal, we can have this kind of competition. Now, our costs are very competitive. We're providing access to researchers access to leading edge services and capabilities at more than half the cost for equivalent services. And as you can see here in the chart, as we scale this up, the costs go down. It's a very nice model. And we don't charge for data ingress or egress because all of those costs are already covered by various grants, various research grants. So to sum up, our business model is to create an environment where research and academic users can deliver and consume new innovative technologies and services where the collaborative research is the goal, not profit. And we intend to duplicate this model across multiple data centers, and we'll continue to encourage more technology vendors to participate. And we're planning to onboard even more research. In particular, the AI Alliance is very interested in hosting their work and encouraging their researchers in their alliance to run at the MOC. So in this session, we have a number of talks. In the first half, we're going to be introducing Christy's going to be talking about the foundational services that we deliver and building of that. The second talk will be Min talking about ESI, where we are and how it works. Open cloud hardware, Naveed is going to present how that is being delivered. We'll describe the available hardware at the MOC Alliance and the Open Cloud Network, the capabilities to manage entire topologies of elastic hardware across multiple institutions. And in the second half, we have the Cloud Lab on ESI, LSVD, and getting started with the Open Storage Network. So with that, any questions? Happy to take them. Otherwise, we can move on to the next presenter.
We actually have a couple of questions from the live stream. So Dwayne Branch has asked, is Open Cloud ready for implementation, and how does edge computing happen in this setup?
So first question, the answer is yes, Open Cloud is ready for implementation. In terms of edge, the way I think about edge would be just like other data centers. But there are different considerations, so I'd want to pull on that a little bit more. I don't have a clear answer. It'll depend on the different types of use cases they're talking about and how big is the edge. Are we talking about a branch office, or are we talking about just a smaller data center? If it's a smaller data center, then the answer is the same. That's how we would just extend the open cloud to the multiple data centers. But if it's much smaller, then there's different considerations to make. Any other questions? Okay. Thank you. With that, I'll bring Christy up to the stage.
Hey all, thanks for coming here. I'm Christy Nicola. My official title is written up there, but I've been working with the MOC since 2015. I was an intern back then, and I had the task of deploying our first production OpenStack cloud. That's an insane task, but thank you. I guess it worked out. I'm here talking about it, and since then, I've served as the chair of the OpenStack Technical Committee, and I've also served as the project team lead for the OpenStack Identity Service, which is called Keystone, and a lot of the contributions and lessons that we've learned along the years have flown back to the upstream community, and especially in Keystone. So what does it take to provide a cloud service? Like, you'd think that you have just deployed your OpenStack or your OpenShift and you're done, right? But no, you have to allow users to sign up, advertise the services available, allow users to request access, allow users to grant access to other users, invoice based on usage, give support when users need it, have visibility into the inner workings of an open cloud, because that's one of our goals and is very important for us, and quickly scale this up or down as demand grows or shrinks. And at this point, you're probably screaming internally, like, help. So that's what I mean by foundational services, and I'm going to talk about more in this presentation. So I'm not talking about OpenStack, OpenShift, Cloud Lab, Dataverse. I'm just talking about the services that make it possible for an open cloud, or any cloud, honestly, to offer these services to their users. So in a way, you can think of this as the infrastructure for the infrastructure. So they can be broadly categorized into identity and access management, so user registration and authentication, and project and allocation management. Then there's a consumption-based billing, telemetry, and I will be focusing and talking about these first three, but there's also support and facilitation, and you heard Wayne talk a bit about that yesterday, and bare metal provisioning, and you're going to hear that in the next two talks. So let's dive right in. Identity management. So we want to enable users to use one single identity across the services of the open cloud. We need to support them authenticating using their institutional credentials, but we also want to allow enterprise users to authenticate into the open cloud. To achieve this, we're using Keycloak. It's an open source identity provider. It supports OpenID Connect, which is an open standard for authentication. And it's what we are exposing as the interface to the services that are going to be and that are part of the open cloud. Both OpenStack and OpenShift support OpenID Connect, and if you're using the NERC today, that's what you're using to authenticate. And if an application that wants to join the open cloud doesn't support OpenID Connect, well, it should. So we've paired that up with CI Logon. CI Logon supports over 5,000 identity providers, including campus identity providers, GitHub, Google, Microsoft, and ORCID. CI Logon is operated by the National Center for Supercomputing Applications at the University of Illinois. So the above combinations make this possible. So you can see OpenStack and OpenShift up on the screen, and they both present an option for authenticating via OpenID Connect. And our project and allocation management, which is shown at the bottom, also supports logging in with OpenID Connect. So once a user clicks there, they are presented with a selection based on which university they're at. And if you are, as me, a BU affiliate, then you're going to see the familiar BU login screen. Hopefully you remember the password. And after that, you're going to be allowed in, and you can make use of the services. So, but authenticating is obviously not enough. There's access management, which is the second piece of identity and access management. So we need a way for PIs to see which cloud services are available and request access to them. We've implemented this functionality on top of an open source software called ColdFront, which is developed by the Center for Computational Research at the University of Buffalo. We've developed an open source ColdFront plugins that implement support for both OpenStack and OpenShift. We've also implemented a plugin that provides a REST API interface, which we've made heavy use of, especially for registering huge amounts of users for the classes. And all of this functionality is open source, and you can make use of it. So how does this work? PIs can create projects. They can grant access to other users or delegate management responsibilities to this project. Once they have a project, they can also request access to the cloud platforms and services that we make available. We define this level of access as an allocation. So ColdFront and the plugins that we have developed handle the responsibilities for creating the required access control permissions so that the PI and its users have, say, a project in OpenShift or a namespace in a project in OpenStack or a namespace in OpenShift and are able to authenticate there and make use of these resources. It also deals with quota and limits and like sets the baseline for how much of the resources that we have available you can consume. And a project may have multiple allocations on multiple services, or it may have the same allocation, multiple allocations on the same service. And user memberships to these allocations is separate and managed by the PI or the user to which they have delegated this responsibility to. So here we see a view of what requesting access looks like. So there's a text box for the justification for why you're requiring access. There's a drop-down providing a listing of all of the services that we provide. Right now, it's only OpenStack and OpenShift that is available through ColdFront. And this is a view of an example project. So it contains 2 people there. You can see the role that each of the members have. And there are 2 allocations there which are expired. So this is a test project, but this is the view that PIs will be presented with, and it's fairly easy to use, and we've had good feedback. So great, now we've got people having access to the cloud services. It's time to make them pay. I think you got away with it long enough. So we've implemented a pipeline for doing this so that each PI gets an invoice for the resources they have consumed in each of the allocations that they are using. So this is on a consumption-based. We've needed to define what's the fundamental unit for which we're going to be billing for, and that's the service unit. So we've defined what a service unit is for each of the services that we're providing. So for example, an OpenStack CPU-based VM has like 1 vCPU and 4 gigabytes of RAM, and that's a service unit. If your VM has 2 vCPUs and 8 gigs of RAM, it's going to be charged for 2 service units. And if you're using a GPU, you're going to be charged for 1 GPU service unit, either for OpenStack or OpenShift, and the same for storage on the gigabyte level. So finally, we've implemented tooling to collect that information, additions, multiplications, simple math, and each PI gets an invoice based on what they are using in the cloud. So it's also important to have visibility into the inner workings of anything that you're operating. That may be a simple Python application, but it's probably even more important when you're operating a big cloud. So we're collecting metrics and logs using Prometheus and Loki, and we're using Thanos for aggregating this information and storing it long term. And we're using Victoria metrics for storing this even more efficiently and even more longer term, probably until Ragnarok. Finally, Grafana is used to build shiny dashboards in a way that allows us to transform the data into something that we can gain information and insights from and we can action upon. So we're currently collecting this data on both OpenStack and OpenShift, although only the NERG OpenShift data is flowing into Thanos for long-term storage. And here's a diagram with a lot of arrows and boxes, as most service or microservice architectures tend to be. But fundamentally, we're getting most of these components through the Red Hat Advanced Cluster Management, and especially its observability service. So each of the clusters has a Prometheus and metrics collector, and the information flows into Thanos. So we can now use this data to see how students are doing. We had a heavy influx of students. And this is a graph of student use of OpenShift AI for classes. You can see a max of 327 containers, so it seems we're doing pretty good. And we can try to gain more insights. For example, this is a graph showing the change in consumption of resources. So you can see the spikes of usage and when they happen, so we can make sure we're prepared for the inflow or cleaning up after the students. And if you're too lazy to go to Grafana, well, we'll find you on Slack. So you can get alerts like this on a daily basis. But our vision is to enable an open cloud, so a multi-sided open cloud with multiple participants across organizational boundaries. So we want people to start offering services in the open cloud, and we want them to plug into the open integration points that we're providing in authentication, allocation management, and telemetry. So all of these interfaces are open to anyone, and they are standard. So there's OpenID Connect, there's Skim, there's Prometheus. And we want to encourage a collaborative environment rather than an adversarial one. So through this, we want to increase the pace of innovation that is possible with open source, but not only open source. So we want to shorten the time that it takes for code to make it from the developer's machine to the cloud, where a specialized or experimental service can be provided and gain access to scale or to specialized hardware deployed by hardware vendors. For example, we had Lenovo stand-up racks of hardware on our data centers. So this is becoming a reality now, and participants in the open cloud will have access to these specialized resources, and researchers can make experiments using specialized hardware and even offer back experimental services. So this really makes the feedback loop that Oran described yesterday possible finally. And we also want other data centers to join us in the open cloud, but I'm an open source engineer at heart. I want all of this to be reproducible. I want all of this to be open source. Probably Oran will get upset about this, but I am an open source engineer. So everything we're doing is open source. You can use our work. You can create your own open cloud. There is no secret sauce here. All of the code, Kubernetes manifests, container files, Ansible playbooks, all of the tooling is available. And finally, what's missing? Well, we want to make telemetry data more available to PIs and users for the resources that they're consuming, but also to researchers. And we also want to collect more data, so from more systems. That's part of our vision. We also, we're currently building users once a month, but we want to be able to allow showback and reporting so that PIs can see usage on a real-time basis of the resources that they're using. Another thing we've started to think about is direct billing to users. Currently, everything flows through the institutions, so we have no ability to directly bill users for usage in the open cloud. Well, what else? We'll see. We're going to find out as you join us, and we build this cloud together. Thank you. Any questions?
So I've been actually using the system to run 3 research projects, and I have to say one of the key properties that I've found has been great has been the adherence to APIs that let me write my own scripts, and I'm not bound to any particular interfaces. I know how to write my own scripts, and I've been able to automate both the use of our GPU systems and our non-GPU systems for our work, which has been fantastic, and also I've been really happy with the ability to allocate storage, and right now your pricing model for me has been fantastic, which has been, you haven't created a bill for me, so I'm thrilled with that too. But just something that you mentioned towards the end that I think is really super critical, so just want to add my voice to the need for it. I really want those interfaces so that my scripts will automatically know what my current account charge is and automatically throttle whether I'm going to let my sub-users go. Because that's the other thing that I found very powerful. The stuff we've done, all my students and my researchers do not know about any of this, right? I've hooked it up so that I played a little bit of SSH magic, they SSH, all of a sudden for them, the SSH all of a sudden stops and says, oh, I'm sorry. Wait a couple of seconds and the machine will be ready for you. The machine comes up, they're in. But I don't want them in if my account is running low. So those interfaces would be really important to me.
You get it.
Okay.
So how hard is it to do congestion pricing? And how much can be exposed? Can I say I want to run my job only at 9 a.m. when no one else is running?
So the building blocks are there. It's just a matter of assembling all of them together. Because if we're collecting the telemetry and we see when the spikes of usage are, then it seems reasonable that we are able to do that. It's just making it a priority, putting the work to get it done, and doing it.
One of the problems is that allocating VM resources is sticky. Once you get the damn thing set up, you want to keep it going. And so how do you like roll or back up or roll off a VM so that it doesn't actually take up any resources, but you still have it around for when your allocation of billing is now coming together?
So for OpenStack, if you're booting from a volume, then you can delete the instance and preserve the data in the volume, and then the next time around you can spin up another instance. We're pretty cheap on on our storage level, so I think that should be the way to go, putting the data in storage and then spinning that up again.
A question about carbon footprint. We have more and more projects where we kind of need to instrument how much power we are using, and I'm wondering if in Prometheus you have ways of adding sensors to report on power usage, and eventually also temperatures inside the machines, to have an insight on how much cooling has been used for matching the power.
I do not have information for that right now. Perhaps Thorsten does.
It's not yet included. Sorry. It's not yet included, at least not on my side, but I would love to have this, so it's in a plan, yes. We will have it. We will have it. The plan was like it's not there yet, so yeah, it's a definitely plan. It's a must.
So you get it too.
So I have one question, Christy. One thing I expected you to talk about is the cultural aspect between the open source community, what hasn't been happening, can you talk to that at all? You know what I'm talking about.
Yeah, so I mean that's part of the feedback loop that I'm describing here. It takes a long time from submitting code upstream to having it actually in use in your data center, solving the problem for which you contributed it upstream, and that's really stifling the desire on my part to make contributions just based on how long it will take for that to come back to me. And on a similar level, there's no way for us to get the same level of either information or users and I'm talking about me with my open source community hat here, not like my MOC engineering hat. But like having access to a large pool of users that is not locked into a walled garden with high egress costs, and like not giving you the information of how the users are using your services, and it makes it really hard for you to like stand up any experimental services to try and figure out what works and what doesn't. Or even worse, like stealing that information from you and providing a competing service like Amazon has done a lot of times. So like we want to create a level playing field where everyone can like try their hand at innovation, be them a small scale, be them one singular engineer, be them a larger company. It's just really powerful to give that sort of access to the level of users that we have, and having those integration points where we have done the heavy lifting for you, and you can just come here and give us a rack of hardware or give us your endpoint for authentication, and we're going to deal with the rest. And we're going to give you a bill for your users. You don't have to think about it.
We have one more question over here.
Hey, just a quick question about the identities. So Jonathan mentioned, he does some SSH key machination on his own. How do you have to have a common identity scheme and kind of system in order to deal with sub-users and actual users and kind of end users? Is there a lot of complexity there, or you found you can just delegate it to the PIs or whatever?
So in this case, Jonathan was talking about like the authorized keys in a VM. We don't deal with that. We're mostly talking about the API level or the dashboard level, like where you are able to authenticate into the cloud and then spin up new VMs or other VMs. If your users are getting direct access to the VM through an SSH key, we don't see that level of permissions. Like you're free to do whatever you want with that. It goes like, it bypasses us in a way. So our authentication level is at the API, and it's using OpenID Connect. You can do what you want.
We have another question from the live stream. Dwayne Branch is asking, are serverless applications possible?
They are, and I think we are investigating whatever OpenShift provides for serverless. So we're perhaps going to have more information soon about that. But I know that we are experimenting with offering function as a service on top of OpenShift.
I have one here. Are we open to the next question? I have a question here, and I'm sorry if I interrupted something there. I just I grabbed the mic. I'm Doug Berry from Lenovo, and my question relates to demand, because one of the things we're doing with the MOC is to provide hardware as demanded. There seems to be a lot of GPU interest in the community across the board. We just installed 64 A100s for the MOC's use, and it's being turned up here shortly. But I'm kind of looking to query the crowd. We're looking to try and get H100s into your cloud too, and I'm just trying to gauge, is that of interest, and how much interest? Because it is very interesting across the world. They're kind of hard to get. But if we were able to provide those, would you be able to use them? Because we're trying to gauge what's next and get ahead of demand. So I'm kind of polling the room here. Is H100 very interesting to you for that?
Lift your hand if it is.
Okay. And remember, we have A100s there today. They're turning them on now. I don't know if the access time, but they're in there. So we'll work to get H100s for you too.
Yay.
To that point, if we're going to make those, so right now I'm using one of the A100s. We do have to have a better understanding of the cost model there, right? Like those are expensive for me, and yet right now the basic model is if I own the VM, I get paid for it as long as I own the VM. But so it's actually 2 points. One to the authentication issue. So what we do to manage that, it's not actually just the SSH keys we're doing. So I, as a PI, have chosen to get a key. So, you know, the standard thing is I download one of their certs, strings, and then I have embedded in my own scripts that then I hand a secret to my users. That then lets them on demand spin the VM up, but then they use their own key to go into the VM. But I, as a PI, have decided to go with that model. And I'm very careful not to let the secret for the CloudFront, my CloudFront API access point, leak beyond my users. But that's just a choice how we chose to do it, rather than authenticate each one with their own CloudFront key.
By the way, Tara, was there any response online about people that wanted the GPUs?
You had the right diagram up a second ago. So when you're doing the systems research, how does the infrastructure get partitioned so that there are parts of it that are under development, parts of it that are under testing, and then parts of it that are going to be production, so that people who can actually are getting billed for it aren't going to get screwed when you add a new feature into the system? And how do you do that I don't know, development life cycle in the current version?
So it depends on the kind of system research. If it requires bare metal, you're going to hear about that in the next talk, where we talk about bare metal provisioning. But yeah.
So if you're doing actual systems research and you're coming in and, you know, working on a new systems capability, you're not going to be charged at the maximum right off the bat to experiment. So, you know, obviously there's a limit to how much of that we can do, but it's recognized in the OpenShift environment. We can build your own cluster for that kind of experimentation. You know, obviously not 1,000 server cluster, but and in the bare metal cluster, we're going to have a whole talk about that piece. In the OpenStack, it's a little more complicated, but at least for sure in the bare metal and in OpenShift, you can do that.
So I have a question about, I guess, I haven't really tracked the latest in OpenStack and OpenShift on this front, but something that draws people to public cloud, the major public cloud providers a lot, is data warehouse technology. So things like BigQuery and Redshift and Snowflake and so forth. I'm wondering, you know, what are the options available in OpenStack, OpenShift, this kind of stack? And, you know, will MOC have a sort of data warehouse equivalent to those technologies at some point in the future, or does it already even?
So right now we're using the Nessie for storage, so it is possible to like make use of the Nessie offerings or spin up other offerings on top of Nessie. So you heard yesterday talk about Dataverse and how it can access data sets directly from Nessie. And if you want to stand up a new data warehousing technology and integrate into our integration points, then you are going to appear in the dropdown and users are going to be able to use you. We're just starting out now, so we have S3s through the OpenStack service and access to the Nessie Ceph. So that's what we have right now, but this is this is changing on a daily basis. A lot of exciting announcements yesterday and today, and it's hard to keep track of everything. So, great question.
Hey, so my name is Suman Chen. I'm a software engineer at Red Hat, and today I'm going to talk about ESI. So what is ESI, or Elastic Secure Infrastructure? And there's a variety of ways you can think about it. The principal one is it's a bare metal cloud that's designed to be used by multiple tenants. So in this model, in the single ESI instance, you might have a bare metal cloud where all the hardware is provided by one organization, or you might have multiple organizations pulling their hardware together into a single ESI instance. Regardless, the base principles are the same. Owners have exclusive use of their hardware, but they can also offer up their hardware for lessees to use. Lessees can see these offers, they can claim these offers, and they can claim these nodes, and once they have access to the nodes, they can provision their own bare metal clusters on their private networks, and that's the secure part of Elastic secure infrastructure. When the lease is up, the lessee loses access to the node is cleaned, and the node is just returned to the offer pool. The other way I like to think of ESI is really just OpenStack. So it's Ironic, the bare metal service, Neutron, the networking service, Keystone, Identity, Glance, Image. And yeah, we get the benefit of the enormous OpenStack ecosystem, and a lot of things, a lot of the requirements we have were just fulfilled just by virtue of being part of OpenStack. So it's been really great for us. So you can think of ESI really as just as a specific configuration of existing OpenStack services. That being said, we have developed a few tools on top of OpenStack to help us out. The principal one being a leasing service, and what that lets us do is just track leases and make it really convenient for us to see like which nodes are being used by which projects, and look at lease history and things like that. The other extension we've created is the extension to the CLI. So what we discovered is that with the base OpenStack CLI, there's going to be a lot of operations you want to do, like attaching a node to a network. And using the base OpenStack CLI, you'll need like 5 to 6 CLI commands. And it can be a little bit complicated and very intimidating if you never used OpenStack before. So we've extended the CLI for ESI, and so commands like that now just take a single command, and it's been really great for our users. So who's using ESI? And this is something that we've worked on a lot in the past year or so, setting up a production MOC ESI instance, and really encouraging users to use ESI and getting their feedback and understanding how we can make ESI better. So the current production MOC ESI users, they kind of fall in one of two categories. The one is grad students from BU and Northeastern, and a lot of these users have been migrated from Hill BMI, which is the old bare metal allegation and provisioning system. So the typical workflow there is that a grad student project comes to us, they request some nodes, and we allocate them some nodes. Then they'll create their private network resources using the OpenStack CLI, and then they'll provision their nodes using Metalsmith, which is an upstream OpenStack bare metal provisioning library. Once they're done, they'll network their nodes using our ESI CLI, and then they'll basically be done with ESI. They'll have their own private bare metal cluster, and then they'll do things of which I'm not fully cognizant, but there's things like distributed storage research and operating system experiments and unit kernel experiments and stuff like that. Again, I don't really know the full details, and kind of I don't really need to. I just need to know they're using ESI and they've used it to set up their environment successfully, which is really great. Our class of user right now is OKD, and OKD is an upstream version of OpenShift. Initially, when they came to us, we allocated them 12 nodes, which they use in 2 different OKD clusters. Each cluster has 1 bastion host, 3 masters, and 2 workers. One cluster is used as a build cluster, and so they stood that up a while ago, and it's just been running ever since. The other one is a CI cluster, so that one gets torn down and rebuilt nightly as part of their CI. We've recently given them access to 30 additional nodes, which they can claim elastically, and their plan is to claim them and use them as part of their CI pooling service. And what I understand their CI pooling service is they have this service which consists of a variety of bare metal nodes, some of which they own and are local to them, some of which they've acquired from other sources, and now they have access to our ESI nodes as well to expand their CI capabilities, and that's really cool. So the way they use ESI is there's a developer on their staff that's really experienced with OpenStack, and he created custom scripts that use a combination of the OpenStack SDK and the ESI CLI commands to configure and deploy their nodes. There's also a couple of projects and ideas that I've mentioned to us that have been driving our development. One is Cloud Lab, which really wants to lean into the elasticity of ESI, being able to claim nodes and put them into their test bed and things like that. I'm not going to go into too much detail there because the manual is going to talk about that a little bit later. And then you see a variety of other projects here. And one thing that they all kind of want to do is they want to be able to quickly stand up small test OpenShift clusters in order to do measurements and experiments and things like that without disturbing their production OpenShift instance. So those are just things that have been ideas that have been brought forth to us that have been driving our development recently. So some observations after this year of usage. So for a lot of users, after some initial questions on how did we use ESI, what do we have to do, we don't actually get a lot of feedback. And our documentation is pretty comprehensive, and we do constantly update it based on feedback. But really what seems to be happening is that many users, they just simply provision their bare metal clusters, and then they never touch an OpenStack or ESI command ever again. And they're perfectly happy, and that's fine. Other users have a lot of OpenStack experience. We give them credentials to access ESI, and they're like, okay, yeah, this is just OpenStack. Okay, I know what to do now. And they create their scripts, and they do their things. And again, they don't really need much help from us. And again, that's totally fine. It's totally great. But what this really means is that it's kind of difficult to identify places where we can improve the user experience. But we still try. So how are we trying to make it easier? The first one is with something called the ESI cluster CLI. And the idea here is that, let's say there's a pretty typical, you want to deploy a pretty typical bare metal cluster, 3 nodes on your private network, and you want to attach an external floating IP to one node so you have external access. If you use OpenStack CLI commands, ESI CLI commands, you need between 5 to 10 commands to do all of this. And if you've never really worked with OpenStack before, again, it's going to be a little scary, a little intimidating, and you'll have lots of questions. The ESI cluster CLI lets you provision that exact bare metal cluster with a single command. OpenStack ESI cluster orchestrate, and then you pass in that sort of configuration file up there. So not only does this make it much, much, much simpler for users to provision their ESI clusters, you just need this configuration file. And you can also share this configuration file with others. So if there's a pretty typical configuration that you're using and other people might want to use, you can just download it and then just substitute your own parameters for your own nodes, your own private networks, and you'll be done. You can just run this command. So that's the ESI cluster CLI. We have a couple of additional commands besides orchestration. There's a list command. So if you want to deploy multiple bare metal clusters, you can use this list command, see your different clusters, see which nodes you're using, and just kind of keep track of where everything is. And then there's an undeploy command. So if you're done with the cluster, we'll clean the nodes, and then more importantly, we'll also remove any associated OpenStack resources like ports or floating IPs. And what we discovered is that if we don't do this, then what tends to happen is you'll start running into the boundaries of your OpenStack quota. So this was a great first step. And then we asked ourselves, can we do something a little bit more? So what we did next is we explored, can we do the same thing with OpenShift? Can we create orchestration commands to deploy OpenShift on ESI nodes? And the answer is actually, it's not that bad. It's pretty straightforward. You just need to use a combination of OpenStack SD commands and OpenShift assisted installer API calls. And you can just pass in configuration file, like the one over there, run OpenStack ESI OpenShift orchestrate, and you will get the OpenShift cluster at the end of it. So that really simplifies the process for a lot of users. We've also added some tools for ESI operators as well. There's the typical reporting tools where if you want to know the status of every node, if you want to know how many nodes are assigned to which projects, you can run a single command and you can get that. The other big thing is leasing history. What leases are active right now? What leases were active this week? What leases were active in the past month or the past year? All these commands, you just run. We have CLI commands to generate these reports in a variety of formats. And I believe that right now we have daily, weekly, monthly jobs to kind of generate these reports for people to see. The other thing we've been looking into is events and notifications. So now, if certain ESI actions will generate an event, like when a lease is created, or when a lease begins, or when a lease expires, We create an event, and then these events can be monitored for various purposes. So for example, we're starting to implement email notification systems so that users have a daily reminder of what nodes they actually have access to, and also reminders when their leases are about to expire, so they know they need to save their information or do other things for their data. So our tentative short-term plans, we want to continue to make it easy for users to script and provision and manage their bare metal clusters. And one way we could do this is to just keep extending the CLI, do things to make sure that our CLI commands can handle more configurations, integration with more applications, stuff like that. I kind of think that is the wrong path to go down because there's just too many different ways people will want to configure their bare metal clusters, and there's too many applications that they'll want to and services they'll want to integrate with. So instead, we're currently focusing on an ESI SDK, and what that will do is it will expose the building block pieces that users can use to create their own scripts. So when the ESI SDK is done, we'll update our CLI to use this SDK, and then when users start using ESI, they can either use our cluster CLI, or if they want something more complex, they can look at our code and figure out, oh, we can use this SDK to do our own thing and then go their own way. Another thing we've been thinking about, and this is actually pretty minor, is the automatic creation of network resources. And that's just when a new user comes into ESI, they always have to create their network resources, and it's a little bit of a pain. It's not a big deal. And really the only reason I mentioned this is because I brought this up a while ago, and Christy very kindly said, oh, ColdFront actually already does this. Maybe you can use their code. I looked at the ColdFront code, and it's like, yeah, this kind of works. And the reason this works isn't because ColdFront already magically has some ESI integration. It's because ESI really just is OpenStack. So ColdFront works with OpenStack, and so a lot of the tools that people may have that work with OpenStack will just automatically work with ESI. Long-term areas of interest. The first one is really leaning into this idea of having a hardware bazaar. And what I mean by this is that right now, when users claim offers in the MOC ESI, let's say the node is available for a month, and they only need to use it for like a day or a week. They really have no incentive to claim it only for the day in the week. They'll claim it for the entire month, even though they might not need it for that entire time. And so we want to create those incentives for users to think of ESI a little more elastically, to grab the nodes only when they need it, to return them when they don't, and then make those nodes available for others to use. There's a question of security hardening. Right now, the MOC ESI works on a trusted user model where, when you receive a node, you can be assured it's been cleaned, but you can't always be assured that a previous user might not have done some low-level alterations to the node, like changes to the BIOS or things like that. So we have some ideas of how to prevent that, and we've also played with tools like Keylime, which is a node attestation service in the past. Integrating with Keylime, we've discovered is really easy. You just have to set up your Keylime attestation server on a node, create a private security network, and then when you want to test a node, you just have to attach that node to the security network. That being said, not every single node in the MOC has the requisite TPM chips, so there may be other solutions and other ideas we'll have to look into. There's always been the question of a GUI, which is something that we've long avoided. That's something that's just not strictly necessary. The CLI is pretty comprehensive, and we've had a lot of success in just using that. But I know there may come a time when people ask for visualizations or just want an interface that's more point and click, and that's something that we definitely consider doing. And finally, I don't know, there's like, ESI is like a really broad platform, and there's a lot of ways you can interact with it. And so if people have their own ideas, their own interests, I'd be delighted to hear about them. Just come find me, talk to me, and I'd love to hear about it. Thank you. Any questions?
Hi, everyone. My name is Naveed, and I'm a software engineer at the MOC Alliance. I've been with the MOC, I joined them since 2017, so I've been here for a while now. But I'm here to give you a brief update about the hardware that we have at the MOC Alliance. So we have like over 1,000 servers racked at the MGHPCC that are available for people to use. Let's just briefly describe what the servers are. We have 140 Dell FC830 servers, and each of these servers have 4 CPUs, so they make great servers for high-density compute needs. On top of that, we have 440 FC430s, and these are great for any general-purpose use, and they make the bulk of our servers. Then we also have FC630s that like sit in the middle of these two types of machines. The FC830s and 630s have dual 25 gig NICs, while the FC430s have dual 10 gig NICs. And in addition to that, we have a bunch of random Dell PowerEdge servers of various generations that we have had for a while now. And as you heard, we recently got some Lenovo servers. Each server has like 4 GPUs that gives us 64 GPUs. And it looks like we'll get more H100 servers next. And then to connect all of these servers right now, we are using the Dell Z9100 switches. These are 100 gig switches, so that is great. Like, we only need 2 per rack, and we can like break out to connect all of those servers. And like half of these servers have like a terabyte SSDs to boot with, so which is great for fast provisioning and booting. Okay, let me tell you how some of these servers are allocated. So we have like 113 servers are in, we have 100 servers in the Open Cloud testbed, and then another 104 servers in the NERC OpenShift cluster. And currently, these are all statically allocated because we didn't have ESI stood up. So eventually, all of this hardware and any future additions will be only available via ESI. So yeah, for now, we then set up ESI, and I'll tell you what's in ESI. Okay. So we set up ESI, and then, which is basically an OpenStack deployment, as Min described, which is running on 3 OpenStack controllers. That's plenty to handle most of this hardware. And in our deployment, we have 317 servers across 6 racks. And these are a variety of Dell servers of the kinds I described earlier. And ESI is currently managing 14 of those switches. And we are in the process of upgrading our controllers to even more powerful servers just so that we can add more hardware. And the hardware that we plan to add to ESI is another 300 Dell servers. They're basically ready to be added and deployed. And all of this, again, will only be available via ESI's leasing mechanism, just so that we can easily track who has what, and people will not message me on Slack anymore. And that will bring our elastic capacity to 600 servers. Let's talk about storage a bit. So a lot of people who are using this ESI nodes are PhD students and researchers who just want some storage available. And for that, we have a research Ceph cluster, which provides them with a petabyte of storage across 120 USDs. Which would be sufficient, I hope. And for people who want to run like production services on these ESI nodes, they can make use of Nessie. Just like how we are using Nessie for our NERC OpenShift cluster, people can then take these ESI nodes, run whatever service they want, and get storage from Nessie, and that would be more highly reliable Ceph storage from that. So I didn't forget to change my slides. But yeah, that's pretty much it. Cool.
Hi, so my name's Hakan. I'm an engineer on the MOC Alliance. I've been here for about 2.5 years full-time, and most of my responsibilities lie with the network behind all of this stuff, so I'm going to be talking about some of the problems and some of the solutions we've developed for that today. So there's kind of a few problems that we have here. So ESI is really good at dynamic switch port configuration, and it's one of the major reasons why it's so good for dynamic allocation of nodes, because it goes in, it changes the switch port, and sets it to whatever VLANs it needs to be automatically. The other side of that is static configuration. Historically, we haven't really had a system that will allocate, will set switch configuration statically to correspond with ESI's dynamic configuration. So these are things like uplink port configurations and VLAN names and descriptions and things like that are all static configurations that we historically have had to set manually. So another thing is that our network configuration has not been exposed publicly. So, and Christy mentioned this, that our mission is always to make everything reproducible, everything as open source as possible and reproducible. And networking has always been a pretty major missing piece of that. And I think there's not a lot of people that are exposing their network configuration. But it's important when you're setting up clusters like this that if you want to reproduce it, you want to see how the networking is set up on a switch port level. And also network engineers from other organizations may want visibility into how our network is connected, especially the Open Cloud network, because it connects to so many different places. So networks also often have a lot of different vendors and operating systems for switches, especially one that grows at the rate we are. So at the moment, there's not really a way to generically define a switch configuration for different operating systems. Another problem is collaboration. So collaboration is hard if we're just manually configuring switches, because there's no version control, there's no central configuration to view configuration, which is not really how we do everything else at the MOC. So the organization of it is also a pretty big challenge, because there's a lot of different projects and a lot of different connections. You know, our Open Cloud network connects to endpoints at UMass and Harvard and BU, and also for NERC and OCT as clusters, and because of that, there's a ton of VLANs to keep track of. And one of the last problems here is that end users don't have a single place to view node details and network topology relating to nodes. So that's like if you had an application where you wanted to cluster a bunch of nodes together, but your application is concerned about latency or bandwidth, you want to know how those nodes are connected to each other. So that might be one node in one rack and one in another, and it goes through two or three switches to get there. Maybe you don't want that. Maybe you want it in the same rack so that you minimize latency and it's only going through one switch. So that topology is not something that's currently exposed through ESI. We do expose node details, so you can go in through the OpenStack CLI and get that information, but the topology itself is not exposed. So we're going to be using Ansible and some things that we developed on top of that to solve some of these problems. So Ansible is already a proven automation software, and it's got heavy backing from the community, and that's one of the reasons we're making use of it here. So things like DelOS 9 is the operating system that we run on our switches. So Ansible has a module for that already, where we can issue commands through the OS 9 module, and we don't have to worry about that piece of the puzzle. So this solution involves storing switch configurations as YAML manifests in a public repository. So this is very similar to how, for example, Kubernetes manifests are handled in other areas in NERC and other projects, where they are manifests that are stored in a public repository, and then there's some continuous deployment solution on top of that. So we're trying to kind of replicate this in the same way for network configurations. So when we have them in a public repository, changes then become pull requests, and now the collaboration piece becomes a lot easier. And it also allows us to expose those configurations publicly, which is one of the major goals for this. So on top of, we can't just run this through Ansible. I mean, to fulfill some of the problems that I talked about, we have to develop a switch driver, basically, that's written in Python. And it allows us to take generic switch manifests and convert them into commands that are then executed on switches to deploy that configuration. So that's what I'll be talking about today. So the initial work on this is already being completed. The Open Cloud Network is currently being managed by this solution. Around about 600 plus servers and 36 network switches are currently being managed by this management solution for the network. It's managing ESI, OCT, portions of NERC, and portions of Fabric, and connections to Harvard, UMass, BU, and Northeastern are all handled through this. And the GitHub repository link is there if you'd like to visit our Ansible site deployment and see how it works. So how does it work? So we'll talk about VLANs first. So the way VLANs are defined is they go into a YAML file, and you define, like it appears on the right there, for each VLAN ID, a name and a description. And you can also specify whether it's managed or not, which I'll talk about later. So this is read by Ansible as a group variable. So that allows us to say this set of switches should have these VLANs. So maybe the switches in OCT don't need the NERC VLANs and stuff like that. So that allows us to kind of separate the layer 2 environments in the network. So in a similar vein, for port definitions, it's also defined in a YAML manifest as a host variable this time through Ansible. So now we're defining each interface on the switch and defining a whole bunch of fields that I won't list all of them, but there's a bunch available. So the goal here are that these manifests are generic. So we don't want to have a Dell OS 9 specific manifest. We want a manifest that is generic in nature for all the fields. So the only thing that's specific about these are the names of the interfaces themselves. So if you look at the example on the right here, like 100 gig port 130, that's what it's named on the switch. So the idea is you can then take this, and just by changing the interface labels for whatever the switch calls it, you can deploy it on some other switch of a completely different vendor if that switch needed to be swapped or something like that. So it keeps it generic. It also simplifies the understanding of the network a lot. You don't need to be versed in the specific switch operating system to be able to look at these files and understand how the network works. So there's a lot of parameters that are supported. Things like description, MTU, VLAN tagging. All these things are supported, plus a bunch more. Basically, all the basic stuff is supported right now for a port level configuration. So the deployment step uses Ansible. Ansible uses a filter plugin, which is the driver I was talking about. That's written in Python that takes these manifests. It takes the existing switch configuration. It compares them and decides that, okay, I need to remove these configurations and I need to add these configurations. So it'll actually ensure that the manifest is deployed and nothing else in addition to that is deployed. So it truly ensures that the manifest is the source of truth there for what's running on the switch. So you can see an example of an Ansible task there that calls the filter plugin for that. And on the bottom, you'll see what the output looks like, which is just an example, 4 lines. You see the switch name and the commands it's running on the switch to deploy that configuration. And lastly, we've recently completed development of a continuous deployment solution. Taj at Red Hat completed that work. He's over there. This is a Python application that's containerized. It allows us to listen to the repository where the manifests are stored, and when it detects changes, it'll actually go out and deploy those changes and then report via Slack success failure, any messages associated with that. So this continuous deployment solution isn't deployed at the moment, but we're hoping to get that done pretty soon this year. So that's the kind of last piece of the puzzle to get this to be a full pipeline. So for future work on this, We want to support additional layer 3 configurations. Our network, because of systems like ESI and Cloud Lab primarily using it, are very layer 2 focused. So that's kind of what we designed initially with this is layer 2 configuration. So we don't really have a ton of options for things like BGP and layer 3 ACLs and a bunch of stuff like that switches do support, but we don't support them in the manifest. So we'd like to add support for that. We also don't have support for system level configuration at the moment. So things like spanning tree bridge priorities, which are tied to the system itself and not a specific port on a switch, and also global like VLT or MLAG configurations that the OS 9 calls MLAG VLT. So stuff like that is also a system level configuration. We'd also like to add additional drivers because the goal for this really is to share it and have other people try it out as well. And we primarily run Dell OS 9, so that's the driver we implemented initially, but we would certainly love to develop a Cisco driver because that's a very common brand and a bunch of others, ideally. We'd also like to publish this to Ansible Galaxy. So our repository at the moment is just our own Ansible site, the filter plugins directly in there. So we'd like to split those up and publish the generic portions of this to Ansible Galaxy so that other people can add it to their environment very easily. And lastly, the only thing that this doesn't solve, this solves a piece of the puzzle, but it doesn't solve everything, is that we want to have the ability to dynamically populate our inventory management solutions. So things like Netbox or anything that's user-facing in the future, we'd like to dynamically populate using these manifests, and that way these manifests in this project are the source of truth for not only the admins but the end users as well when they want to go in and see topology for things. Are there any questions?
Okay, so hi everyone, my name is Adam Belay, I'm a professor at MIT, and today I wanted to give a forward-looking talk and talk a little bit about what might be possible in terms of benchmarking the cloud based on the capabilities and environment of the MOCA. So let's dive right into the motivation. So of course benchmarks are incredibly valuable, and it's because they set a target to aim for computer systems researchers. And so often in each subfield of computer systems, you'll start to accumulate a set of standard benchmarks, and over time, those benchmarks will be used as a basis for comparison for different systems in that particular area. And so that really encourages researchers to optimize for that set of benchmarks and to get the best possible performance. And I think David Patterson said it best, for better or for worse, benchmarks shape a field. And in particular, I'm concerned about the kind of negative connotation that's implied in this quote. And my specific concern is that benchmarks only really provide the most value when they can accurately capture the characteristics of production workloads. So that's what I'll be focusing on in this talk. So with that in mind, how good are today's cloud benchmarks? Well, this turns out to be a really hard question to answer because often the most interesting cloud workloads are proprietary or confidential, and so there can be a drift between the kind of benchmarks we're using to evaluate systems and the reality in the cloud. However, on a couple of instances, Google has compared what was going on from a tracing level in their large public clouds compared to some of the standard benchmarks that we're using in the computer systems community. And so I wanted to talk about that and just give a couple of examples of what we've seen so far. Okay, so one example that's really interesting is CPU performance. And here I'm summarizing the results of a paper from Google that was published at ISCA 15. So these are not my results, but I'm just summarizing Google's. And what was really interesting about this paper is they looked at spec CPU and other common CPU benchmarks, and then they compared those benchmarks to the types of CPU benchmarks we're using in the academic community to evaluate performance. And so this is a quote from the paper. The cloud performance was actually significantly different from the common wisdom for optimizing spec-like benchmarks. And the table on the left kind of summarizes what was happening here. So it's actually quite interesting. Most of the benchmarks we're using in the academic community are really well optimized. They have tight loops, very small amount of code, but real production workloads tend to be complex. They have lots of code. Much of that code is part of the active working set of the program. And as a result, it's hard for CPUs to actually cache those instructions. So just the raw working set size of the benchmarks of the real workloads is very large. And so in particular, this puts a lot of stress on the L2 instruction cache of the CPU at an architectural level. And it was actually 15 times higher than what we were seeing in spec. So that's an amazing difference. And what it means is that in the cloud, IPC, that's instructions per cycle, is actually universally low. In fact, it's usually below 1, which is like a pretty low number for a CPU. And so the implication here is that we really need to optimize for the front end of the CPU, the part that fetches the instructions, but that wasn't obvious as we look at these standard spec benchmarks. Okay, so I wanted to give you another example, too, of how benchmarks can be a mismatch from real workloads in the cloud. And this one is a much more recent study that looked at RPC overhead. This was at SOSP last year. And what's interesting here is, again, in the academic community, we tend to use benchmarks that really stress RPC performance, like Memcached and Redis and so on. However, in the paper, they found that latencies in real cloud applications are significantly higher than these benchmarks. And to give you some sense for how big of a difference this is, Memcached typical service time is about 1 microsecond. And on the other hand, in this study, they found that an average or typical service time was hundreds of microseconds to milliseconds. So that's an enormous difference. And I think what it means is that there's been, if we just go by these standard benchmarks, there's been a huge emphasis on supporting as many requests per second and making that as fast as possible. But actually, as it turns out, the optimizations we already have with technologies like kernel bypass are so fast already that we're getting up to the point where Amdahl's law is now in the way, and we actually can't yield better improvements for real cloud workloads. Now, on the other hand, this real data does reveal an opportunity, and that is that there's a huge amount of variability and dispersion in request service times. And so that means the emphasis shouldn't really be on how many requests per second, but rather how good are congestion control policies and CPU scheduling algorithms and overload control algorithms so that we can cope with enormous differences in request durations. And that's what the graph on the left is showing. Okay, so clearly designing good benchmarks for the cloud is really hard. And if these two studies from Google are any indication, it seems like in many cases we're very far off from the benchmarks we use in the academic community versus the reality with real cloud workloads. So I think there are two reasons that make it really difficult to design good benchmarks for the cloud. One of those reasons is that workloads are rapidly evolving. So normally with benchmarks, you can have this process of iterative refinement where you design a benchmark, you can go to industry, you can get feedback, you can adjust it over time to make it more and more accurate. But in the cloud, the actual realities of these workloads are changing every year. And in fact, in Google's paper about CPU performance, they not only observed an enormous difference between standard benchmarks, but they also observed that that difference was shifting pretty quickly every year. So it's actually very hard to keep up with workloads in the cloud. The other thing that I think is really difficult is researchers often don't have access to either the hardware or software in a sufficient level of detail to really design great benchmarks. And so this is what brings us to the MOCA. I think we have an opportunity to actually cross out both of these limitations because the MOCA drives research and open source development on real hardware with real workloads. So this is a really exciting opportunity where we could rethink the way we design and deliver benchmarks for the cloud. Okay, so how can we actually go about doing this? Well, there's a lot of discussion yesterday about the idea of running research systems directly on the MOCA. And I think there's an enormous amount of benefit and value in doing something like this. However, I'd like to argue that this may not be the best approach for benchmarking specifically. And I have two main concerns. So one issue is that it's very hard to reproduce experiments across different runs when you're just running production work as it comes in, because there could be a lot of variability in that work. So that makes it harder to benchmark. And the other problem is that research systems are inherently experimental. So they may be less reliable than production systems, and we don't want to allow failures in research systems that we're testing to cause service outages or problems for other work that we're running in the cloud. Okay, so what could we do instead? Well, the proposal that I am offering in today's talk is this idea of packaging real workloads into benchmarks. And so specifically, I'd like to introduce this abstraction that I'm calling an executable trace. And an executable trace would capture and package all of the metadata needed to run real cloud workloads as benchmarks. Okay, so by having these executable traces, we can now run the workloads as many times as we need to, doing identical work each time, and that provides a basis for comparison across different potential research solutions that we're testing and evaluating. And so again, I think the MOCA is uniquely positioned to do something like this because it has access to real workloads, and also there's enough flexibility that we really could capture these traces in the real cloud infrastructure that's running the production workloads. Okay, so the obvious question then becomes, what kind of things should we capture? And I would like to offer three ideas. I think these are just some ideas among many that we could look at, but it may be interesting to look at serverless workloads and function as a service. We could look at DNN training jobs and DNN inference jobs. We could also look at web backends and capture data that's coming in through a load balancer. And the insight here is that for each domain that we might like to study, these are all domains that tend to have standard cloud computing benchmarks, the metadata that we actually need to record is a little bit different, and it requires us to hook into the system and record things in a different way. So let me give one specific example, in this case for function as a service, and I will use OpenWhisk, which is a popular open source platform for function as a service, just as an illustrative example. So in OpenWhisk, the structure of the system is pretty simple. You have a REST interface where requests come in. They go through a coordinator and through a reliable queue abstraction, and eventually they are delivered to invokers that run on each machine in the infrastructure, and those invokers run a series of containers that execute the serverless functions. Okay, so as these containers execute, they will complete their runs, and those completions will get stored in a distributed database, and that allows the coordinator to keep track of what work has been completed. So if we are going to turn this infrastructure into an executable trace, then we'd want to capture metadata at key places in the system. And so here's some thoughts on where those places might be. First of all, we'd want to be able to capture every request that's provided to the REST interface so we could replay it. We would also want to capture all of the containers. That's the entire image needed to run each program and the exact code and data that we're executing for each function. And then finally, not shown on this slide, we'd also want the raw input data sets that are fed to the serverless functions that they process. So if we could capture all of these things, then we could use them to build an executable trace, and that would allow us to replay that trace, and then we could remove OpenWhisk and replace it with any research system that we'd like to test and evaluate, giving it exactly the same inputs, and turning that load that the service was experiencing into a cloud benchmark. So that's the proposal here overall. Okay, so there are many interesting challenges in doing something like this, and this slide is only scratching the surface, but these are some of the things I've thought about so far. One challenge is just recording the data. So in particular, this is going to generate an enormous amount of metadata, and we don't want to slow down real production cloud workloads because we're trying to capture an executable trace for them. So I think this is a big engineering challenge. How can we record and capture metadata in a way that doesn't interfere with the real workloads that we're executing? Okay, and then another challenge is just the sheer large amount of storage that this will generate. We not only want to be able to store the data efficiently as the workload is running, but we also need to restore it quickly so that it's easy to run these experiments over and over again and try different approaches. And then on the workload side, there are also questions of which workloads should be included in the executable traces. And so it's probably the case that we don't want to record everything. And I could imagine a system where users of the MOC can opt in and volunteer the load that they're placing on the cloud and make it available to researchers so they can improve the efficiency of their systems. And so in this way, when workloads are not open source or they're operating on proprietary things that haven't yet been published, then that could be excluded from these benchmarks. But on the other hand, users could choose to contribute their actual load and make that into a benchmark as well. And then finally, how can users actually run and execute the executable traces very quickly and very easily? One of the biggest challenges for great benchmarks is just how difficult it is for developers to use them. So how can we make it as turnkey as possible and require as little code and configuration for new research systems to play back an executable trace and apply that to their system to evaluate it? And maybe we could even imagine solutions where the performance evaluation and the measurement is actually part of the infrastructure that's provided to the researcher. Okay, so that's it for my talk. This is my proposal, and it'd be great to discuss it, and I'm happy to answer any questions.
I'm going to start with a question from the live stream. So Dwayne Branch is asking, so this FAAS would record metadata for data provenance and in federated learning, or would that be a different need?
Yeah, sorry, could you repeat the question? So,
Yep, so this FAAS would record metadata for data provenance and in federated learning, or is that a different need?
So I'm not quite sure if I understand the question, but to clarify, so for FAAS, I was referring to function as a service, and the goal here is to require all of the metadata you would need to perfectly replay the functions that are executing. So this is not related to a specific ML workload, although function as a service could be used as a platform to execute such a workload. Sure.
Yeah, so great talk. This is very interesting. I'm not sure if you were here yesterday for my talk about Memento.
I was.
It seems like, I mean, the architecture you had up for OpenWhisk, first of all, I didn't know about OpenWhisk. I'm definitely going to take a look. But there's this potential idea for collaboration. So what Memento is trying to do is almost like building on that question from the live stream and a little bit of an inverse of this. You know, Memento is trying to capture all the information that went into a computation, including the provenance, right? And so there's an extension of Memento called Memento Server, the idea being to do that whole thing as a functions as a service. And I can imagine in such a world that we have that kind of server that each of those invocations to a Memento function could then result in a potential package that you could use for benchmarking in the future. So I think this could be an interesting point of collaboration. No question, but I just wanted to sort of mention that we should link up.
Sounds great. Yeah. So what's really interesting is Memento and its metadata overlaps significantly with everything you would need to re-execute one of these workloads for a benchmark. So it'd be great to collaborate on this. And yeah, there's a tremendous amount of overlap. And in fact, Numentos could be a really good benchmark in themselves because they capture so much of what's needed to perfectly recompute the previous job.
Hi, Adam. Thanks so much for the talk. I really think this is a great idea, and I think the idea of thinking about how to integrate this at a more systemic level in the MOC is really useful because, so that specific to the open WISC example, so we did some of that work, and that's exactly what we had to do, right? So we created our own trace points, we then captured it, but we also did it so that we could either capture it at the TCP level and decide whether we wanted to include the network overheads or replay on the node itself. But to that point, I'm wondering whether there's a few things we can do here, right? So one, I think involving the switch infrastructure and potentially logging at points in the switch rather than introspecting on the code. And then the next thing that one might want to do, because I think even in our environment, it's not clear how many folks will do the opt-in or opt-out. So another option is that we build, we get the probabilities and we build distributions based on the trace, and then we generate the trace from those distributions, and that also takes care of some of the potential logging problems, right? Because we can build the distributions as the compression of the trace in the first place. But I think thinking hard about how we could deploy that, and maybe at that switch level, I think would be really cool.
Yeah, thank you for the comments. I agree that doing this at a switch level would be really cool because then you could just have an individual VM or container and replay back the network inputs into it, and that would allow you to benchmark and evaluate it at a different lower layer in the stack that's less aware of the particular cloud programming model. So that's really cool, and that could be a good target point to look at too. Yeah.
Yeah, Shuan from Northeastern. Very exciting, ideas and interesting talk. So, I mean, two things I'm thinking is like, one is that, years ago, we were looking at stuff like with OpenStack, and it turns out like dependency hell is a really annoying problem, right? So it's gonna be a pain in the ass to reproduce the things without capturing all the dependencies. And then let's say you are using ROS projects and your libraries has dependencies of dependencies, you have a bunch of cargo logs. It's like, that's like another side of the problem that you have to take care of. Otherwise, the reproducible problem is it's annoying. And the other thing is, I think for real, I mean, there's lots of cloud workload. There's Blueprint, there's Death Star, or whatever. I think for real cloud workload, one of the problems is something about the specific scenarios they run into, right? So like you said, the Google's workload, that's Google's case. Like if it go to Microsoft, Microsoft will be like, well, that's not true. Like we don't have that kind of problem. And I think it's gonna be like, how do you have those things like baked into the executable traces, but also some way to say like, you know what, this is like different things, and then like these things, they're like, people, you don't want to take that too seriously because then you perform very well on this workload and on that workload doesn't make sense. Anyway, just some thoughts. It's yeah.
Yeah, those are all really great points. So one thing that concerns me as well that overlaps with this is the workload characteristics of the MOC might be different from the workload characteristics of hyperscalers. But I think that's okay. I think if we can target real workloads that people are using and then orient our benchmarks to capture those behaviors, we're already moving in a step in the right direction where they're becoming more valuable. So that's one of the reasons I'm really excited about this.
It's just like, I think MOC would be a great starting point, right? So it would be interesting that Google says, well, we want to run these things here, and then see what that shows. So.
You were mentioning the effects of caching at the host level. But we have like 3 or 4 layers of stuff going on here, right? We have the hosts, we got the VMs, and then we got the Kubernetes on top of that. So which level of the benchmarks are you looking at? Are you looking at the Kubernetes benchmarks, or are you looking at the host benchmarks? And if you're looking at the Kubernetes, could you use the Jaeger trace facility to make these executable traces?
That's a great question, and I think it's something we have to figure out as a community. On a personal level, I'm interested in operating systems research. So a lot of the things I'd like to evaluate could be like seen as replacements or alternatives to Kubernetes or alternatives to the kernel. However, there are a lot of really exciting research projects that will also build on that infrastructure and may benefit from direct tracing from that level as well. So I think one of the big challenges is, can we support different levels of tracing and pick the right ones that are useful for a lot of different types of research?
Hi, great talk. I was just curious, it seems like there are lots of research questions around how do you even know that the workload that you're recording and the metadata reproduces the same results, right? And like I was just wondering if you had some thoughts on systematic ways to explore that, because it seems like that's just really cool.
That's a great question as well. So in a correctness sense, we could record and hash, just like was discussed yesterday, the output of the workload and verify that it produces the same answer, and that could help. But from a performance perspective, we may not always want it to reproduce the same result because some of the layers we're replacing might impact how the network works or how multi-core scheduling happens and the order in which things run, and that could produce very big differences. And I think that's okay as long as the end-to-end performance improves. On the other hand, we may also want to study particular layers of the stack, like maybe we have a better congestion control algorithm and we just want to measure network congestion. That seems like a really important workload too. So balancing end-to-end versus studying specific layers seems like one of the big challenges in designing a solution like this.
Yeah, that's great. I was just wondering, like, do you need ground truth at the beginning, right? It's like you reproduced the workload, you recorded it, and then it seems like you might want to be able to replay that in exactly the same system and try and get exactly the same results, and then be like, okay, we changed the scheduling order and all this other stuff, and we got better performance. So I guess I was asking about like that initial thing about recording.
That's a wonderful point as well. So a lot of real systems, including the Linux kernel, have this phenomenon called performance hysteresis, where you can run two different experiments with the same inputs and the same data and get very different performance results each time. And one actual research goal is building and designing systems that don't behave that way and are more consistent. So this presents a lot of challenges where you really need a lot of runs and a lot of statistical significance to draw conclusions, and that also is one of the challenges. Again, I think the experimental infrastructure that records and replays the execution traces might be able to help researchers with that by automating some of those difficulties. Okay.
Okay, folks, we're going to take a short break here now, and then we'll come back at 11 o'clock to finish off our morning session. Thank you. folks, if you'd please come in and take your seat, we're going to start back up.
Yeah, we're talking about you, Michael. Yeah, whichever way you are. It's Italian, but I'm French, so nobody knows how to pronounce it.
Oh, really? That's an Italian?
Yeah, it's Cecchetti in Italian.
Oh,
My grandfather was Italian. He fled Italy when the Second World War started.
okay. That's not when my great-grandfather came a little bit before that.
Then everybody moved to France. And in France, they don't even know how to pronounce that. So it has been like, yeah, story of my life.
I was in Lesordo. I'm a born Lesordo.
Oh. Nice.
I liked that name better.
Well, when I got married, I'm like, to my wife, don't take my name. It's
Too difficult, right?
yeah.
Are there people out there? Okay, folks, we're going to start the second part of our morning session with Emmanuel Kachet.
Wait for the end of the talk to see if that's really worth it. Yeah, so I'm Emmanuel. I work at UMass. I've been working there for the past 15 years on different cloud-related projects. So the thing I'm going to talk about today is Cloud Lab on ESI. So first, a few words. ESI, by now, if you pay any attention this morning, you should have an idea of what it is. If you don't, you can ask those guys who presented before me. And so we have part of the resources that we use in the cloud that are managed by ESI, that's Elastic Secure Infrastructure. And I'm working on the Open Cloud Testbed, OCT, where they use Cloud Lab as a management system. So Cloud Lab has kind of the main goals as ESI on managing the hardware infrastructure. It's a much older project that started 20-something years ago with EmuLab and evolved over the years. So it's a relatively large code base with a lot of legacy stuff to support all systems. And it has been developed by the University of Utah. So actually the Cloud Lab site that we have here is a satellite site of the Cloud Lab deployment that is kind of centralized in Utah. So what are the motivations behind Cloud Lab on ESI or having Cloud Lab and ESI work together? We have this great data center in Holyoke, Mass, the MGHPCC, where we have a lot of hardware that is deployed. On one side, we have NERC that have their own racks, and they are using ESI to manage the hardware. And we have OCT that also have its own racks and runs on Cloud Lab. And actually, Oran brought that up one day and said, well, I'd like to be able to share some of those resources, take the NERC rack, make them available to the Cloud Lab users, and when they don't need those machines anymore, we can put them back in NERC and use them on ESI. And the problem is that those systems originally are designed to have exclusive access to the hardware and manage their own hardware, their own switches, their own nodes, and they are not made to share racks between each other. So the idea of this project is trying to see, can we just put hardware in the data center and make it available to everybody and just move it around? So for this to happen, we have basically two problems to solve. One is who is owning the hardware at any given time, and how can I lease the hardware to some other user and then reclaim it back? So we're going to see the lease mechanism in ESI that are actually great for that. And once we have actually given ownership or the rights to another lessee to use the hardware, how do we make sure the two systems can cohabit in racks or sharing some of the hardware and be able to run together on that hardware. So here on the slide, you can see we have NERC that is running on ESI. We have OCT running on Cloud Lab. And so the idea is to deploy ESI everywhere and have Cloud Lab run on top of ESI. So now we just have a single management layer for all the hardware, which is going to be ESI. And we're going to try to modify Cloud Lab to make it run on top of ESI so that we delegate all the hardware management function to ESI. And that has a number of challenges, but in the long run, that's also solves a lot of problem when you have to onboard hardware, add new hardware to systems. You don't have to do the work twice of finding drivers in each environment to make the hardware work and reconfigure everything to the databases, etc. So ESI has a great mechanism of leases and offers. So let's say NERC owns hardware. So I have some comments there you can see on the top right. NERC can decide to create offers to offer some of the nodes to Cloud Lab. And there's this ESI offer create command, and you can say, I want to offer my nodes to Cloud Lab for this time period. And each node gets an offer associated to it. And on the other side, Cloud Lab can claim those offers and get ownership of those nodes for the specific period of time. And while the Cloud Lab has claimed ownership of the nodes, it will retain exclusive ownership of the node until the lease expires, meaning that no other user will be able to use those nodes. Here we have exclusive in quotes because actually the ESI user can do still operations when the nodes are leased, but in the if you think about it, it's like basically we give the node to Cloud Lab will be the exclusive user of that node until the lease expires. So what I'm going to talk about now is the prototype implementation we have. It has nothing to do with the current production system. We have NERC running ESI with their own machine. We have a OCT deployment with production nodes. Here we created a small test bed with 16 nodes. That is accessed both by Cloud Lab and both ESI, and we have a development environment for each. And so the idea is to say, we have this mini environment, we are going to take those 16 nodes from ESI, share them to Cloud Lab, have Cloud Lab use them, and at the end, give them back. So here we have 16 nodes that belong to the Cloud Lab ESI demo user, and if I do the node list command in the OpenStack console, I see my 16 nodes available, and the one at the bottom here is what the view that you have on Cloud Lab. Cloud Lab doesn't see any nodes. You do a bare metal node list. You don't have any hardware available because you haven't claimed any offer yet. So the offer list, I can see all the offers that are available for those nodes. So the next step is for Cloud Lab to claim those nodes. So there's an ESI offer claim command where you can claim the nodes, and once the nodes are claimed and you try to do a node list, you will see that actually leases have been created. So that's the ESI view of things after the nodes have been claimed. There is a lease that is created to each offer that have been claimed, and we can see the name of the lessee here. It's Cloud Lab who has claimed those nodes. So now if I am doing my OpenStack bare metal node list on the Cloud Lab site, I see my nodes that have been offered to me, and I can do whatever operations I want, pixie boot them, turn them on and off, etc. I own those nodes. I can deploy whatever I want on them. So now that Cloud Lab has bare metal hardware, Cloud Lab has to make those nodes available to its users. And so there's a process whether you are in ESI or in Cloud Lab, where once you have hardware, you go through an inspection process, make sure the nodes are actually up and running so that you don't offer nodes that are not working to the users. And so in Cloud Lab, this is called the OS reload operation. And so you reload all the OSs, it's going to try to pixie boot system and make sure everything comes up online. And once all the nodes are, have been gone through that process, when you go in the Cloud Lab web interface to reserve nodes, so here you can see that the Cloud Lab GUI, you can go in the and say, I want in Massachusetts to reserve some of the hardware. The hardware we're using are those 16 FC430 nodes, and I can put a reservation on them and claim those nodes and then work with them. So once the, let's say those nodes were given to us for three months or 6 months period, at the end when we have to give the nodes back, the only thing that is really needed from the Cloud Lab side is to delete the leases. So the leases can expire. If you had put a fixed end date, when the lease expires, they are automatically returned. If you want to return them early, you can just do an ESI lease delete. And then the nodes are, now you can see the offer. If the offer hasn't expired, it can still show up. If the offer actually also has an end date that has expired, all the leases get cleaned up and the offers disappear. Here, if the offer is still open, that means Cloud Lab could try to reclaim those nodes again and lease them for another period of time. But once the leases have been deleted, you can see the bare metal node list returns an empty list because the nodes have been returned. So what did we learn so far doing this little experiment on plugging Cloud Lab on top of ESI? So the first thing is about the hardware. We got a lot of donations of hardware for the different clouds we are running at MGHPCC, and every time we get a different kind of hardware, there are headaches on finding the right drivers, finding the right configuration and the right setup to make those server works. And so when you have multiple managing environments, you need to do the work for each of them. So you have to figure out a way to make those nodes work in ESI. You have to find a way to make those works node in Cloud Lab. Cloud Lab is even more challenging because it's a very old software stack. They are still using FreeBSD, which has very limited drivers for some of the more modern hardware. Like even the FC430s we are using in this demo, Cloud Lab is not designed to boot anything on to use 10 gig on the management networks. It tried to force the links to be only 1 gig. We're kind of lucky for this experiment that the hardware was so new that it wasn't in the exception list of FreeBSD, and they were like, we don't even know what it is, so we're going to try to boot it, and that kind of worked because it wasn't hardware they couldn't manage properly. But there's always challenges in trying to get onboard machines on those different environments. It's still a very, very manual process. So the approach we have right now of running Cloud Lab on top of ESI, Cloud Lab originally was just developed in Utah to manage their data centers, and then when they started to add more data centers, they have the option of you can book resources like 2 servers in Utah, 2 servers in Wisconsin, 2 servers in Massachusetts, stitch them together, create your own VLANs to connect those resources together, which means they have to have control on all the switches on the network path to set the VLANs and stuff. Here we are delegating the VLAN management to ESI, which means we cannot, ESI cannot control the rest of the Cloud Lab network. So the approach we took for the network design only allows us to share resources within the Holyoke data center at MGHPCC, but we cannot stitch those resources with remote sites. on Cloud Lab, which is not a big issue, but it's a current limitation of the approach. The great thing, though, is that now if we can make the entire network stack of Cloud Lab run on top of ESI, we don't have to deal with populating the Cloud Lab database with all the MAC addresses and all of the stuff that is needed to access the bare metal hardware. We can just give the IDs of ESI and let ESI manage all the details of accessing the actual hardware at the bottom. So it's still work in progress, but we have a good testing environment now to complete that implementation. Part also of dealing with old software and bunch of scripts and stuff is that this is academic software that has no testing environment, no test suites, nothing extremely hard to debug. So progress is always slow. It kind of. I'm sorry. Yeah, I'm talking about Cloud Lab. Yeah, no, I would love, and that's that's the software that is developed in Utah. The great thing with ESI is that we have all the Red Hat folks that are here and being very active on the development, and it's much newer software with a much newer design. When you are dealing with legacy software, is always much harder. So. One thing I'm hoping now is that, especially with all the interfaces that ESI is exposing to us, we'll be able to automate the resource discovery. I can pull from ESI the list of nodes that are available, just put that information in Cloud Lab and say, those are ESI nodes, you don't need to know any other details, ESI will manage that for us, and simplify a lot of the onboarding process and management process. One of the paths we could go that's still would be a very long-term goal would really have to have a network switch driver for ESI in Cloud Lab. There's still some more work to be done on the interfaces for that to happen, because Cloud Lab really expects to see a switch, port numbers, VLAN assigned to ports, etc., where in ESI, you are more manipulating networks, attaching a node to a network. Yeah, the VLAN is attached to that network, and you can try to network together, but it's not really a vision of a switch with ports like you would have in a traditional network. So I think the goal of this is so that we can have people donating hardware. They don't have to think as like, oh, should I give hardware to NERC or to OCT? Is like whatever hardware you are gonna you are gonna contribute to the platform, we can easily move it and make users have the best use of them between the different platforms, and we can dynamically put them to Cloud Lab users, NERC users, OCT users, Fabric users, or any other framework that's gonna give access to those resources. So. That has been definitely an interesting experiment. It's still ongoing, and we're hoping that hopefully by the end of after the summer, we'll have a completely running platform and be able to move the nodes between the two platforms. Thank you. Any questions?
First of all, thank you for your talk. So I have a quick question. In your demo, you mentioned like ESI offers the bare metal resources and Cloud Lab actually claims those resources. So is it true otherwise as well, so that we know like Cloud Lab is now working on top of ESI, but whenever ESI wants some resources, it can just ask Cloud Lab and claims those resources from Cloud Lab. So is that possible? And based on that, can ESI provide those resources or lease those?
There are two ways of doing this. The ugly way is just to say the hardware is down, and then it's flagged in the database and it's not available to users. But a cleaner way is to say we have an ESI user that can have a priority in the scheduling mechanism, and say we are blocking all those nodes for the ESI users for that period of time. There's still a limitation that Cloud Lab expects to have exclusive access to the switch. So it's easy to share an entire rack with a switch at the top. When you start to want to share just half of a rack with someone else, there is still only one switch managing all the machines that rack at the bottom. And sharing the admin of a switch for just few ports is not something that is easily doable, especially in Cloud Lab. It's much more flexible to do that with ESI.
So this is great. If I ever would have realized how hard it would be to integrate this, I don't know if I would have promised it that a couple of years ago, but it is. I just want to kind of set the stage for the three talks and what you did here. I mean, so when we were looking at Cloud Lab back when it was, we as systems researchers, would use this platform. It's incredible. It's been incredibly valuable for us. But now when you have a whole bunch of hardware that's for a specific community that all has the same publication deadline, what do you think happens before the publication deadline? In fact, we saw that in the first year of usage, is that before OSDI deadline, the hardware was incredibly highly utilized and nobody could get access to it and stuff. So this idea that we could shift hardware between them, at the end, I think we're hoping that everything is in ESI in the whole data center, and then there's no issue of sharing because you can just hand it out to Cloud Lab or to NERC or to OpenStack or OpenShift or to OKD or all these, or even the HPC clusters eventually. Kind of the goal is that we can move the hardware to wherever it's needed before whatever deadlines they have, because we'll have fairly large numbers across the whole stack. I mean, there's more questions for specifically Cloud Lab on top of ESI? I mean, this was heroic work. I did not realize how complicated this would be. I think we should all give Emmanuel a big clap for this. This was pretty impressive.
Also, I think something I would like to convey to everybody here is that some software is not necessarily that is the most popular, is not necessarily the best software. So there is always a question of timing when things are ready to use on a specific platform. But documentation and user interfaces are very important. Now, I've seen that I've been for more than 30 years in this field. Sometimes it's a software that has the best documentation, the best support, and the best interfaces that people use, and it's not necessarily the one that have the best technology underneath. And so I think that ESI is very close to taking over everything, and now I think the emphasis is really on making better documentation, maybe more user-friendly interfaces building on top, which are very easy things to do rather than re-engineering everything under something old.
So I guess we should clap for Min too.
Next is Peter. Oh, more questions? Oh, sorry, there's another question.
Emmanuel, so it was fascinating, the story about all the interesting use cases or corner cases rather that you ran into while making ESI work with Cloud Lab. Can you extrapolate from that general design principles for systems that should work well with this kind of with a model where you shift resources from one system to another?
Yeah, that's a very good question. I think the way Cloud Lab is a lot of legacy code that was originally designed for small clusters like stuff we had 25 years ago, where we didn't have cloud. It was really just those start of those HPC clusters, and everything is still SNMP in there. It's same FreeBSD as I was doing, and I was using during my postdoc 25 years ago. And people just, it's an academic project where you had people running in every year and piling up patches on top of patches on this piece of code. It's still amazing that this thing still runs actually today.
Yeah.
I think the main issue with the Cloud Lab design is that a lot is still centralized in Utah. So even if I want to onboard nodes in Massachusetts, they have to update the database manually in Utah. We can't even do that. They have to add that information in the database in Utah and push that back to our local database in Massachusetts that is actually just a cache of that.
Yeah.
And it's really meant as a centralized system that is very hard to distribute or run your own instance. Where ESI, for example, if you have your own data center, it's easy to deploy and have your own setup running independently of anything else. Cloud Lab cannot run without a connection to Utah. So that's, I think after that, picking whatever environment you need for managing your data center is going to depend on the skills and the knowledge that your staff has for that. And making things interconnect with other data centers or other systems, it's also a lot of human factors that are involved. Admins don't like to share passwords. They never trust each other. Interconnectivity needs also a lot of political influence at the higher level to make things happen. And it's like, yeah, no, you guys have already to work together to make those interconnects. I mean, I think ESI right now is probably the easiest and best solution to get the hardware management from all the frameworks I've seen so far. But software also evolves over the years, so it's great to have a team that can be behind and follow the evolution and not get stuck in old designs that are super hard to refactor after a while.
Yeah, well, thank you. I didn't mean to put you on a spot. It's just, it's fascinating work, and I think we could probably stretch based on your experiences, things that you encountered while making this work with Cloud Lab to gain insight into how design flexible systems in general would be a fantastic result.
So some of the problems that Emmanuel's pointing to were, they're very specific Cloud Lab. We actually had a couple of students doing projects to try to elastically move things, and I drunk the Kool-Aid where I believed that all these systems were intrinsically designed so a hardware node could fail or a bunch of nodes, and so we could use those mechanisms. Yeah, it wasn't so easy. You know, there's the inventory system that every one of these things have, where they assume they have a static inventory, they own it. There's then, even though they can kind of fail at a certain granularity, there's the scheduling gets all messed up when a node goes away because they don't actually have it on their normal critical path. It took a lot of design at the layers above. A student that was doing a marketplace to move things rapidly. It was, so it is going to take, I think that it's really important, the comments you make is to start expanding the principles, you know, not just the remote database and things like that, but also, and part of the work that, you know, for example, you saw today is we're trying to build an inventory system so that there's a source of truth so we can provide to everybody, and then they only know about the nodes they have right now. Right, so a lot of these mechanisms we're gradually building up as we get experience, because NERC has to acquire and release these nodes, not just stand up a new cluster on top of it for OpenShift or OpenStack. And it's going to be a while till anybody builds into their base mechanisms the concept that these actually production clusters are really themselves elastic. So it's harder than we thought it was going to be, or we knew we'd run into issues, but I don't think we expected it to be, the platforms that were deemed to be elastic and fault tolerant would be quite so hard to integrate this elastic hardware. And right now, it's okay because I think we're talking about a matter of, you know, moving nodes, you know, days, for days at a time. Eventually, we'd like to do it at a much finer granularity than that. you know, capture binaural patterns, have machines in a cluster for hours at a time or even less. And in fact, what Peter's going to talk about is mechanisms we've been setting up for disaggregated storage to have things be able to be in there for very short periods of time in the cluster. But it will take time to propagate this up to all these higher layers. So we're building the plumbing.
One more over here.
So does the Cloud Lab give you geographic extent, and NERC is only right now in Western Mass, right? That's the only data center that NERC has, right? So if I wanted to do one of these edge computing research, would Cloud Lab be the sort of the input into the NERC big cloud?
Well, that's way above my pay grade because, but, I mean, the things that I've seen in Cloud Lab, because actually in the Cloud Lab interconnects between the different data centers, you can use OpenFlow and program whatever network protocols you want. So they have focused on the networking aspects for folks that were doing research in networking. I think here we're more focusing on just running workload on the machines we have. Actually, even the interconnect of the Massachusetts site to the rest of Cloud Lab, the uplink connection is pretty limited to do that kind of connections. I think it's not even working at the moment, if I remember correctly. So it's really meant to, most of the users we have of OCT on Cloud Lab are just reserving and using nodes in the MGHPCC and running their experiment within MGHPCC without trying to stitch them with other resources outside this Cloud Lab site of Massachusetts. So, but I think there is a connection between OCT and Fabric at the moment. So there is a connection between those nodes you can get in Massachusetts to the rest of Fabric. But between NERC and OCT, I don't know what the plans are. I don't know if Oren has a comment on that.
So eventually, we're hoping to incorporate other data centers in this kind of open cloud model. Right now, I mean, NERC things can clearly communicate with, you can get bare metal machines on OCT, and we can directly communicate through, you know, internet with, but it's within the data center with NERC. But I don't think that was the question. It's more about the geographical distribution. And the only story now is Cloud Lab, yeah. And Fabric, of course.
So
and Chameleon, of course.
And
yes,
Chameleon,
sorry.
yeah.
So do you see the ESI as like a virus that might expand out to the Cloud Lab to get a new generation of software on it? Because you were complaining that the old generation needed some upgrading.
I'm not sure I got the question. Could you repeat that?
So ESI is a new generation, lots of backing between it.
Yep.
Can you see that software being incorporated into the OSI or into the Cloud Lab software, because you were complaining that Cloud Lab was old at this point, the software was old at this point?
I don't see it being incorporated in Cloud Lab in the sense that it would require way too much refactoring of the software. The best we can hope is having a ESI driver pretty much in Cloud Lab so that we can run ESI managed resources from within Cloud Lab. I think that's our best hope. There are still challenges. There's going to be challenges and limitation even in that implementation, but I think that's our best hope.
So I guess I disagree. So I was talking about this with Rob a lot when we were sort of kicking off this collaboration, and I think that, you know, there's basically if you take OpenStack or OpenShift or Cloud Lab or all these different projects, they kind of couple the allocation of nodes, some of the network, the switch control, and the provisioning of things all together into offering an end-to-end service for for all their different things. And fundamentally, the premise behind this work is that we can decouple these things, that we can actually have the allocation of the nodes and sort of the fundamental switch control decoupled from all these environments that provide very powerful services for a particular user community on top of that physical hardware, and they can do their own provisioning of the physical machines and everything else. And I think that, you know, Rob would be very excited to do this because it sort of removes one layer of stuff from his project, and we can build that as a fundamental layer. You know, we're not there yet, but that's where I mean, the point is that we first built the foundation here for ESI. Now we're doing our integrations into OpenStack, OpenShift, and OCT. And yeah, that is our hope, is that this becomes kind of a fundamental layer under these other things. But I wouldn't call it a virus. I'd try to be a little more positive about it. Sorry, Emmanuel, do you disagree with that, or is that?
Yeah, I kind of disagree in the sense that the Cloud Lab software is not a modular software. Like ESI, you have those modules, and you have those specific pieces of code that have specific tasks, and everything is mixed in Cloud Lab. It's like just scripts coding each other piled up like this. So if we extract the hardware management layer that ESI is doing now, there's so much rewriting that it's like, why not use the rest of the components you already have on top of ESI, and why try to refactor and re-engineer the entire Cloud Lab? Is probably going to be more work than just using what you already have. So it's not like we can simply extract the Pixie boot part of everything is intertwined with the switch management and stuff, and everything is calling each other, and it's a super, I mean, it's an old software that was designed almost 25 years ago, so, and it has never been refactored, so it's not like a modern software where, yeah, you have modular pieces that you can replace and improve and change, so it's much more challenging than that. But in concept, yeah, I'd love to have, just remove the hardware layer from Cloud Lab, put ESI instead, but it's not going to happen like that, unfortunately, with the way the software is designed at the moment. Okay, I think we have to leave the, we are out of time and need to give the, but I'll be around for the rest of the day, so if you want to talk and stuff, we can follow the discussions over there. Thank you again.
So just really quickly checking, I'm told that sometimes the clouds don't update themselves. Are these not? Yeah, no, these are not up to date. Okay. So, yes, please, rather than. Hi, I'm Peter Desnoyers from Northeastern, and Isaac Kaur, one of my PhD students, and we're going to be talking about our virtual disk project, which actually ties into a bunch of things, including we're actually hoping to use this with the elastic hardware, with ESI, because we want, and that's someplace where we really want to achieve, local hardware level performance. Let's see, I think, okay, great. So to start this off, the motivation for this work actually was a number of years ago. In the Mass Open Cloud, we tried running OpenShift on top of OpenStack. And I had never in my life before seen 5-second disk IOs and 99-point-something% IO wait time on the back-end machines. It was a catastrophe. And what we discovered, and I'm sure a lot of other people have discovered, is that, basically that Virtual disks are a great way to take fast, expensive storage and turn it into moderate speed, even more expensive storage, or to take, moderately priced storage and turn it into really slow, but still not very cheap storage. And if you're trying to build a cloud, especially an open cloud where you're scrambling around for funding and donations, the massive amount of equipment you need to throw at getting good virtual disk performance is really a problem. And basically, virtual disks are everywhere. I mean, virtual machines run on virtual disks. A huge fraction of the cloud of internet services is virtualized. They deal with writes with workloads that are very difficult. Small writes, high write throughput. Isaac has some stats on this. And really, as a cloud user, they're basically still the best way to get raw storage. If you want to put a storage service on top of someone else's cloud, you're stuck with putting your data on, you're often stuck with putting your data on a virtual disk, and you have to deal with its performance. So in this talk, we'll talk about cloud workloads and virtual disk workloads, some about existing solutions and why the overhead in Ceph RBD, the LSVD architecture and experimental results. And so this section is going to be Isaac discussing his work, and then I'll come back to discuss sort of advantages and lessons from a 1,000-foot level.
So what we've been building, as Peter mentioned, is a virtual disk for use in modern data centers and cloud workloads.
Can people hear?
A little louder.
Put the microphone closer or something.
This should be better. Oh, there we go. Right, so in order to build a virtual disk that's ready for modern data center workloads and for cloud storage workloads, we want to look at what cloud storage workloads actually are. And so this involves trace analysis of traces people have released. And the surprising thing is that there is a surprising lack of high quality traces out there. As we see here, the most recent paper from 2023, a bunch of people from Chinese University of Hong Kong analyzed a trace released by Alibaba from 2020, which turns out to be the most recent high quality trace available of about 1,000 disks. And then we have a Tencent trace from 2018, and then a trace from 2007 of Microsoft Research Cloud, which is probably not of use and not representative of anything we might see today. So what they have found in their trace analysis is that, for a cloud workload, most of your operations are writes. And the reason for that is caching works, right? You see that you have a lot of read workloads, you put a cache in front of your service, and then you serve most of your reads from the cache. So everything else that doesn't reach the cache, turns out most of those operations are writes because you have those things must get persisted. So over here you can see that about 50% of all of your disks have a write to read ratio of about 10. So 90% of all of your requests are actually write requests, and about 20% of your disks actually have that over 100 to 1 write ratio. So 99% of all of your requests are writes. So it turns out when you're building a cloud storage system, you're really optimizing for writes because most of your disks spend most of the time writing. The read is handled from layers far above where you're handling. And the key thing about most of these writes that we're discussing is that most of them are really small writes. Right? Maybe it's a database writing something or a file system updating the inode table or some kind of metadata operation. But the key thing to realize is, across, not Microsoft Research Cloud, but across everybody else, that most of the writes, over there are the median write size for both of Tencent and Alibaba turns out to be, 4 kilobytes, 8 kilobytes, maybe 12, right? So the vast majority of your writes are small. And for most of these cloud storage volumes, it turns out they're also very bursty, right? Application developers are used to being able to request pretty much however many IOPS they want from the backend, and that leads to results like some of the disks have a burstiness ratio of 100 to 1, which means that the peak IOPS and the average IOPS is off by a factor of 100. So a disk, might have an average throughput of 1,000 IOPS, and it might scale up to 100,000 IOPS at peak and then go back down. Right? That's true for individual volumes, and even in aggregate, you have significant variance in peak and average IOPS. Of Alibaba reports 2 to 1, and Tencent Cloud reports roughly 1.6. And Microsoft Research Cloud from multiple years ago have 7 to 1. So our ideal virtual disk would have very good small write performance, would be scalable for burstiness scenarios, and it would be optimized for writes primarily, and would be compatible with existing systems and are quite efficient compared to existing systems. So what's wrong with Ceph RBD, right? RBD is the current solution that most people use, and it's provided by the Ceph project. And the main problem we have found with using Ceph RBD is that it has a large degree of write amplification. What we mean by that is every single write must be replicated 3 times in a normal triple replicated pool. So every time a client makes a write, however small, it first goes to the first OSD, and then the first OSD must replicate it to 2 other OSDs. Both of those OSDs must do journaling or metadata writes, or all of the bookkeeping to make sure that you retain consensus, right? And then once all of those are done, then you can finally acknowledge the write back. And this leads to a very high degree of write amplification especially for small writes. Right? Over here we have a study from 2017 by a bunch of people in Korea where they found that for Ceph Blue Store, which is the current generation of this, the file backend, the object store backend for Ceph, is that small writes have a write amplification factor of almost 15 to 20 times. So a single client write is amplified 20 times into 20 backend writes, and that holds for both SSDs and hard drives. So it turns out small writes are really, really expensive. And so as Peter has previously mentioned, what this does is it turns, for example, 100 disks, each of which has 150,000 IOPS for aggregate throughput of 15 million IOPS. You've converted that, you just divide 15 off of the aggregate IOPS straight off the bat. So a 15 million IOPS cluster, just because of amplification factor, the maximum you can get out of that is 1 million IOPS. So this is how we're turning a lot of expensive storage into not very fast expensive storage. Right? And this becomes even worse if you have a spinning hard disk, which are still quite popular for mass storage, but a hard disk might have 500 random IOPS, and if you divide that by 15, you don't really have any left. So which is why hard disk performance is not very good for a lot of these virtual storage systems. So what we've done is with LSVDs, we're taking all of these into consideration and seeing that we need to optimize our small IOPS and for write performance. And what we're doing here is the main thing is that we're batching up all writes together into larger batches and then shipping that back to the backend as larger writes. So what we're doing is we built our list to be log structured, which means all of the writes go into a write log, and then the write log is only occasionally all written to the backend in giant batches. So if a client makes 100 requests, we batch all of those 100 requests into one giant request, which is then written to the backend. Right? This leads to much better write efficiency because we're not constantly hammering the backend with tiny small writes, and instead we can cache all of the writes on much faster NVMe drives, for example. And then one of the other things we do is we put all of these on a storage gateway to intermediate between client writes and server writes. And what is with that gets cut off with NVMe over Fabric, right? So an NVMe, which is most modern machines will support NVMe protocols, and as long as you have the correct drivers, will be widely compatible with most virtual machines that need storage, right? So also by putting on the gateway, we can scale, right? We can deploy more gateways when more performance is required, and we can scale it back down when we don't need as much performance in times of low demand. Right, and as we see here, it's very easy to spin up new gateways for handling higher performance requirements. So what we end up with is an architecture that looks like this, right? A client connects to the gateway over NVMe over Fabrics, right, which is run over SPDK, and then we turn all the writes into, we journal all the writes on a remote write journal, and then we serve all the reads from a local read cache. If all of those miss, then we actually read from the backend. And there's a subtlety in where we choose to put the write journal over here, because obviously we can't put it on the same machine as we can't put it in RAM for one, because if the machine crashes, all of your data is gone that wasn't written to the backend. So that's not an option. One option is to put in local NVMe, which is the simplest option. But if that machine crashes, now you have downtime as you get a sysadmin out there to recover the NVMe drive and put the machine back up. So the choice that we ultimately ended up with is putting the write journal on the remote NVMe drive. So that way, if a machine crashes, right, you can just immediately spin up another gateway server that replays the log on that server, and then we can immediately carry on with a very little downtime. And then for people with higher redundancy requirements, you can put a second NVMe drive and mirror those two NVMEs, but that obviously has a cost in both performance and storage, so that's not what we've done for the evaluation. And another cool thing we can do with such an architecture is that clones and snapshots are essentially free because we have a log structure where everything is just append only to the end of the log. Clones are essentially a fork in the write history. So if we clone at block 3, then blocks 1, 2, 3 are shared between all of your clones, and only if you continue writing, then all of those are forks. So even in the read cache, for example, if we have a bunch of Ubuntu VM images, for example, that all share the same glibc and all of your libraries, then they all come from the common base image, and they don't take up any additional cache space. So now I'm going to talk a bit about our evaluation of how we perform against primarily RBD as our point of comparison. Our test setup is we evaluate both on an SSD pool and a hard drive pool. In the SSD pool, we have, it says 48 here, but it's actually 16. We have a 16 SATA hard drives, 16 SATA SSDs, and 48 SATA hard drives. And both of those are pools where we put all of our storage on for both RBD and for LSVD. And the primary thing here we want to look at is that, how do we compare in our performance? And it turns out that, the main thing I want to focus on here is for the write performance because, we're optimizing for writes. And, the green is LSVD, the red is RBD, and we're basically much better than RBD in both a random and a sequential workload. Right? On SSDs, we're 2 to 3 times better. On random, we're much better in sequential because it turns out that RBD doesn't handle sequential workloads very well as they all hammer the exact same OSD at the same time. But for hard drives, you can barely even see RBD down there because, hard drives performance, as we said, are not very good. And if we can aggregate all of our writes on the NVMe drive, we will just have much better performance than, RBD can muster. And for reads, the primary thing we're looking for is that we're not any worse, right? And unfortunately for random reads, that's the only time we're worse than completely random reads with a cache that's not sufficient to hold the image size. That's the only time we're worse than RBD for the main reason that we have a lot of cache thrashing, right? We have newer optimization that will detect this and then automatically bypass the cache and when we detect that the workload is too random for a cache to be of any use. But in all other cases, we do essentially on par of RBD as in the hard disk case, or much better if we have any amount of cache locality and we can cache all of the backend objects on our gateway. And this graph here shows how we scale with multiple clients and multiple gateways. And the main takeaway here is RBD is very good at letting a single virtual disk essentially take over the entire performance of your Ceph backend, right? If you have 100 OSDs, a single virtual disk that is big enough can very easily saturate the entire available IOPS space of the backend. So going from 1 client to 4, 1 virtual disk to 4 doesn't really help you in scaling up performance because a single virtual disk already takes up all of your available performance. Whereas with LSVD, because of internal map locking structures, adding more clients and more virtual disks actually improves our performance in the aggregate by quite a bit because we can scale more with more clients. And then the same story with adding a second gateway, actually, right? Because most of our performance comes from writing to a local NVMe drive or caching on a local NVMe drive. If we add a second gateway, as long as that second gateway has access to a sufficiently high performance NVMe drive, we can also essentially double performance compared to RBD that has already saturated the backend. And the last thing I want to point out over here is that we're much more efficient than RBD at both reads and writes. Right? Here we have a random read and random write workload, and we measure the aggregate CPU seconds used essentially across a single workload. And over here, LSVD is about 30 times more efficient than RBD when it comes to backend CPU utilization. Right? RBD here uses almost 1,700 microseconds per client operation for a random write, whereas we use 58. So we dramatically improve our write performance by the simple fact we don't take many trips to the backend when we write. So if we look back at our requirements for what a good virtual disk for a cloud environment will do, right? We have achieved small write performance. We have achieved, our virtual disk is write optimized, and we're I/O efficient. And all of those come from our log structure, from batching writes together and shipping up to the backend in larger batches. And then by putting all of this on the gateway, right, we have scalability for very, very, very bursty scenarios, and then we have minimal coupling between our hardware performance on the back end and our virtual disk performance, and we also achieve very good compatibility with existing systems just by using NVMe over TCP. And I think I'm handing it back over to Peter for the larger picture.
All right. So I wanted to, step back and talk some about Isaac's results and sort of what it means for us, in Mass Open Cloud and hopefully beyond. So basically, well, and before I go to that, I also wanted to back up to here. So the thing here is, it's not just that RBD takes almost 2 milliseconds per I/O of CPU time, it's that it does so many I/Os as well. So this was using dozens of CPU cores just to satisfy I/O on one virtual disk. So what this comes back to is, we're trying to eliminate write amplification, we're trying to decouple capacity and performance, and then I'll also mention endurance management. So basically, we're starting from, RBD and, other systems like that. They're doing everything all at once. You send a write out, and they're making sure they've got write-ahead log for consistency, they're updating metadata, they're doing all these operations. Instead, in the, in one case, we're doing a single journal write, or maybe we're doing, a replicated journal write, and we're handling, and because it's a log, there's going to be a lot of complexity on failure to recover, but for the expected case, we're doing, we can just do that 1 or 2 writes. And then we can batch things and amortize the cost of full stripe writes across the back end, and get much more performance out of the same amount of hardware. We can take the expensive high performance drives and use them for the write journal and for the read cache, and then we can keep piling more cost-effective drives up to build up capacity instead of having to pay that performance tax on every terabyte that we put into the system. So that's the key thing. We're decoupling, the performance storage on the right and the performance storage on the left and the capacity storage on the right. We're also pulling the CPU usage out of the back end as well. It's to achieve the high throughput, really high RBD write throughput, you actually need a lot of CPU power on the machines that are holding those drives. And then if, once the I/O dies down, there's no way that you can use those cores for anything useful. They're just sitting there. Instead, we can pull that off. And so if you need, so, where the solution in the fully decentralized RBD style picture is you would have to, beef up each of those machines and pay a tax on, your whole storage pool. Here, we can add resources just in the gateway, just when we need it. In fact, if we disaggregate the read cache, we're able to take generic compute machines and repurpose them to add performance here as needed. And then if the I/O load drops, well, you can move them back to using them for VMs. An interesting thing that's come up in the last is also it's really useful for endurance management, because it turns out there's a lot of things nowadays where you want to have a write journal in front of a bigger storage system. QLC Flash, I'll talk a bit about that. That's a big example. The problem is that, well, Optane's dead. And this idea of having a tiny write journal in front of a really big back-end storage, there's a problem. If your back-end storage is 10 times bigger than your write journal, then your write journal needs to have 10 times the endurance of the back-end storage. And a factor of 10 is small. You could easily want to have a journal 100 times smaller. So it turns out it's a really good thing to be able to put that write journal in one place that doesn't take down all the rest of your storage system when you rotate it out because your NVMe drives there have reached end of life. You know, as the last of the Optane in the universe gradually gets sold off and used, this is going to become more and more of a problem. It turns out this approach works great with QLC Flash as well, because QLC gives us sort of the write performance of hard drives, but the read performance of, you know, real Flash. It's, you know, they do insane things to be able to pack 4 bits into every cell. And so if you want to write less than 64 bytes at 64K to QLC, well, you write 64K. It's got incredibly low write endurance. So this idea of a write journal of doing very large, you know, full stripe writes works out very well. And you know, so finally, to you know, what we're using this, you know, at this point we're working on trying to get this to the point of deploying a pilot in, you know, with ESI and hopefully accessible to NERC sometime during this calendar year. We want to go further with it. We see, you know, we see an opportunity for something that's, you know, significantly, well, more than significantly faster, way faster than the other approaches that we're able to deploy on the same hardware, both for virtual machines, for containers, and even for booting, you know, for booting bare metal hardware. In particular, the gateway here is we're using NVMe over Fabrics, NVMe over TCP, and so as the target we're providing, that lets us hook up directly to various hypervisors, but you know, with some effort, with modern enough machines, we can just boot off of that. We can also do an iSCSI target for our older donated hardware. And you know, that lets us treat our bare metal nodes like you treat a VM, something that you can power off, give it to someone else, and then later on boot it up off of your disk image, not theirs. So anyway, the LSVD approach gives us far higher performance. It lets us do a full caching without the consistency issues of other write-back caches. It delivers hardware level performance to users without them having to tie themselves to either, you know, devices on a bare metal machine or, you know, local SSD on a VM. So, you know, you're able to, it reduces one of the barriers to doing storage services as a tenant rather than the provider. You know, nowadays the deck is sort of stacked against you that as a user of a cloud, that the provider gets to deploy bare metal machines and build storage services. You sort of can't. So I guess that's all, and you know, I wanted to thank Isaac for his work and see if anyone has questions.
Let me add one quick comment to this. Just what was really important about this work is to ESI doesn't really make sense to do any rapid pace beyond days at a time or something if you're actually using, or for that matter, Open Cloud Test, but if you're actually using something like Frisbee to copy the entire image onto the machine. You know, you need disaggregated storage. You need to have virtual disks in order to have elastic hardware. And so this is a kind of crucial building block for us. We're getting near the performance of if you had a locally attached SSD to every machine, but it's actually scalable. You can add more or less of them, and we've totally disaggregated the storage. And now what we're doing is working with Christy. We're going to, we're working with the IBM team on this, but we expect to have a prototype of this up on at least one node on every rack in ESI, so that we can offer this experimentally and start using this for things like NERC as it kind of evolves to give us that disaggregated storage so we can rapidly move machines around. So it's kind of one of the key values that we're trying to build here is we can build research, we can experiment with it, we can deploy it for services, especially all the Elastic experiments, and then kind of go from there. So deploying the innovation into our data center with real workloads.
Yeah, I mean, this is actually a great example of, what we really wanted to do with the MOC from the beginning is, a problem that came from the MOC, research based on it, and then we're finally, after maybe more years than I ever thought, rolling back around to being able to try to deploy solutions, coming back from that original problem. So questions? Lars.
I would say it's all the code is on GitHub, right? And I would say the stability is a bit sketchy right now.
But you could bring up it's an SPDK-based server, and so and the back end is Rados, so you can point it at a Rados pool, you can run the gateway, and you should be able to mount volumes off of it and so on. It's been a little while since, there was a period of time when we did extensive testing of rebooting VMs in it and so on. It may have regressed a little bit since then when we did the performance tests.
Yeah, the recovery path especially is a bit sketchy, so I would not trust any real data to it at the moment.
That's true. Before we had done a whole bunch of things like crash tests, and then we did performance tuning, and we haven't done the crash tests again. Other questions? Thank you.
All right. Hello, everyone. I'm Chris, and I'm the Deputy Director at the Massachusetts Green High Performance Computing Center. Can you guys hear me okay? Is that better? There we go. All right. So I work on several cross-cutting projects regionally and nationally around cyber infrastructure and workforce development. And the project here I'm talking to you about today is a national effort called the Open Storage Network. And much like most projects in this space, we have our own three-letter acronym, or TLA. So I'm going to use the term Open Storage Network, or OSN, interchangeably. So data is growing at an alarming rate, right? Whether that's telescopes or microscopes collecting data at unprecedented scales, sensors or IoT devices aggregating data, or you taking disparate data sets and aggregating them to do training, the need to capture, store, share, and analyze data is constantly increasing. And so the Open Storage Network originally focused on data sharing, but as you'll see throughout my talk, we've sort of adopted and provided other solutions as people expressed interest in doing more with the storage network. And so to think about OSN, let's take a step back and look at the United States research cyber infrastructure ecosystem as of today. So within the National Science Foundation's portfolio of services, they do a really good job of providing local, regional, and national resources for compute, particularly in that HPC batch workflow workloads. And those systems are pretty much standardized. In the networking space, we have over 200 universities at the 40+ gigabit scale, and of course, network is very standardized as well. But in the storage space, storage is mostly balkanized, right? The National Science Foundation doesn't provide many storage services at the national level. They tend to fund campus storage, which more often than not is a POSIX storage system, right? Sometimes proprietary, attached to an HPC system. However, most science projects are across institutional boundaries, and we have a need to share data. And so what you end up doing for these projects is either getting access to another campus's VPN and IAM solution, but more often than not, you end up doing shadow IT and setting up a Google Drive or a Dropbox or a Box or a OneDrive, and you probably have multiple of all these for your different projects. So OSN tries to do that by building a cyber infrastructure storage service that provides low-friction data sharing services. So the Open Storage Network is our national resource for sharing open scientific data. We have a distributed infrastructure and governance with simple and flexible access and management controls. So here's a map of our infrastructure throughout the United States. Now, initially, we started with some funding from the National Science Foundation, Dalio Philanthropies, and the Schmidt Future Foundation, and that funded our initial pods, which are along with our initial founding members and also participants on the operations side of OSN, and that's San Diego Supercomputing Center, that's NCSA at Illinois, that is Johns Hopkins, that's RINCE in North Carolina, and the MGHPCC. Now with those, we built our original Generation 1 pods, which were about a full rack of equipment, about $150,000, and provided about a petabyte of usable space. But now, since that NSF project has ended, and we've developed the infrastructure around supporting these in sort of an automated CI/CD fashion, we now allow other organizations to buy their own hardware with their own funding, and then we federate it into the network and provide sort of object storage as a service. And so we've been very successful over the last couple of years getting funding, particularly from the CC STAR, the Campus Cyber Infrastructure under SICE at the NSF, under their data storage program. So we have 4.5 petabytes going in at Caltech libraries later this year. We just put in production some storage at Rice. We have a storage solution for Alabama A&M that was funded by that program. We have 3 storage pods, or 4.5 petabytes of storage for the American Museum of Natural History in Manhattan. The University of Rhode Island has a pod here at Markley Data Center in Boston. And then the U.S. Geological Survey has 2 pods, or 3 petabytes of storage at our data center at MGHPCC. And so when talking about data, it's often good to look at the FAIR guiding principles, right? Findable, accessible, interoperable, and reusable. And we've historically focused on the accessible part, right? Sort of standard protocols for authentication and authorization. And we have some other activities going around to automatically process storage buckets and generate a persistent metadata view of that bucket. And we also have some activities around registering our OSN-provided storage with some national data storage, data location services to make it findable. But historically, we have focused on the access part of it. And so basically what OSN is, it's S3, right? It's S3 storage if you've ever used AWS S3 or another S3 storage. It is a publicly routed data lake. So if you can access the internet from where you are, you can access your OSN storage, right? It's all over this RESTful API riding on top of HTTPS. For authentication and authorization, much like all these web services, it uses an API key pair to access the service. However, we've wrapped that around ColdFront. So earlier, I think it was Christy's talk, who was talking about NERC and the ColdFront portal. We have the same thing here for OSN. We have a cold front portal where you log in with your campus credentials via CI logon, and then from there, you can retrieve your bucket URI, your bucket name, and your credentials for accessing a bucket either read-only or read-write. And then through that portal, you can add other users to your projects, and as long as they have a authentication service that's registered with CI logon, whether that's that campus credentials or OrcID or Gmail or GitHub, you can add them to their project, and then they can retrieve their API keys to do their work. For security and data integrity, this is all built on top of Ceph, right? We use 8+3 erasure-coded blocks in the most recent version of the platform to provide reliability and robust data services. And it's high performance. This is all commodity servers. The original generation was, about a full rack of Supermicro servers. The current generation is, I think, 60% of the cost, and instead of being a full rack, it's down into 7 U's of space and provides 1.5 petabytes of usable storage. But these are all mostly on 100 gigabit networks on Internet 2. A couple of them are at 40 gigabit, and that just depends upon the hosting institute. So the key ideas are a data set is made of a collection of objects. And once you have an object, you now have a URI where you can access that from anywhere. So you either need to use an S3 aware client or code with your API keys, but if your bucket allows anonymous read access, you can access it through a web browser or wget or curl, right? What a lot of people are doing with OSN is they're building project websites using static site generators like Google Pages or Read the Docs. And then their data sets they're putting on an OSN bucket, and then in their static site, their static HTML, which they generated, there's just a URL to download the data sets. And that's one way people are using that to publish data sets. Again, the physical storage, as I showed, is distributed across multiple sites throughout the nation. And we might actually be going international this year. We're talking to some groups in both Italy and Africa who are interested in adopting the open storage network for their solutions. And for the most part, we're located in science DMZs for fast access. We are able to sustain multiple gigabytes a second across Internet 2 from SDSC to our data center in Holyoke, Massachusetts. So usually the bottleneck is going to be on your side and not through the storage network. In fact, from AWS US East 1, you get better performance to our pods at MGHPCC than you do to S3 in their own region. And that's a discussion for another day. So the way data sets are set up, there's a couple of options. Now, Ceph can do a ton of things, right? And S3 can do a ton of things. But we've really reduced the feature set that we support. This is mostly a volunteer effort. And now that we've opened this off and offered this as a service, we don't want to be victims of our own success. So we have a very small subset of the S3 API which we support, and we're constantly adding features as time allows. But right now, we have two sort of data set types. One is open access data sets, where it's anonymous, read-only, anyone can read it, and it's writable by anyone who has the read-write API key pair. Or we have protected access data sets, where it's readable by anyone with a read-only API key pair, and writable by anyone with a read-write API key pair. We do not generate per user key pairs, we generate per bucket key pairs, again, to reduce our administrative burden. Now, as I said, originally, OSN was developed as this low friction data sharing platform, whether that's sharing data with the community or that's sharing data with a project. It was basically meant to replace Dropbox, Box, Google Drive, et cetera. However, as projects started getting used to the concept of the object store, they started building services on top of OSN and not just using it as a means to exchange data. And OSN has now become part of several universities' critical CI plans, right, as a building block for building CI services. So we now allow universities, nonprofit organizations, or government labs to purchase their own OSN storage appliance. So we provide you the BOM, the bill of materials. We very carefully control every aspect of it. We don't allow you to buy part of a storage pod or expand it. It's all quantized, right, in discrete clusters to, again, reduce our administrative burden. And the way we've set up OSN maps really well to the MOC and the open cloud vision that John discussed this morning. So if you remember in John's talk, he brought up this open cloud concept slide where he talked about what defines the open cloud. And the OSN project maps to that vision extremely well, and we have sort of our own way inadvertently also combated that cathedral trend that is in commercial cloud storage. You buy the hardware, you own the infrastructure. Our distributed team of sysadmins, we maintain it for you, right? You get the servers, we mail you a USB drive, a thumb drive. You put it into each of the 3 servers, and that bootstraps them. And then from there, we run Ansible playbooks, and it's all set up, and we run it for you. The operations of OSN is all transparent. We have a weekly implementers team or sysadmin team meeting, which you're welcome to attend. And all of our Ansible playbooks are on GitHub, right? We're very CI/CD DevOps focused. And our cost recovery model, again, we're nonprofits. We're not making any money. We're actually losing money running OSN because, again, it's mostly done on volunteer time. But here is just a comparison of the cost of OSN versus 2 cloud providers. One is Cloudflare and one is AWS for their S3 services. Now, what you can see is we're actually about 10% the cost, not a 10% discount, an order of magnitude cheaper than S3 for more performance. This is actually based on some older numbers, but right now we're around that $16 to $17 per terabyte per year of supported storage. Now that doesn't include the data center hosting costs. If you rate that at the cost of what we charge at MGH-PCC for colo, it's around $19, $20 per terabyte per year, which is extremely cheap for a full service storage solution. So what can you do with OSN and how people are using it today? Well, originally it was very much check-in, check-out semantics, right? Pull down data, work on it, check it back in. rclone is like rsync for cloud storage, command line tool, amazing tool. CyberDuck is a GUI, right, for drag and dropping your publicly accessible data lake. We have a lot of people who are using it with Globus, right, to basically make that as a way for creating a cache for scratch space, right? All our national and most campus HPC systems have a parallel scratch space with a Globus endpoint, but that data's purged every 14 days, right, of inactivity in order to keep scratch spaces clean. And so you can use OSN as a virtual cache as you're doing work. The other nice thing about Globus is it gives you ACL access, right? You can create subdirectories. They're not really directories, but you can create subdirectories in it and then restrict access to individual users or projects within your bucket through Globus. Now that people have started to use OSN a lot, they're starting to update their software and their tooling to be S3 native, right? Reading and writing directly to S3 as opposed to pulling it down to POSIX, modifying it locally and checking it in. And so in the Python ecosystem, there's some native tools which require to use their file formats like ZAR, but there's also FSAILs or file system abstraction layers where you continue reading and writing the file as if it were local. Just upstream in your Python, you say, instead of writing locally, intercept all those I/O calls and write it and read it to OSN. And the package that I use to do that has a great name. It's called Kerchunk, which is a really nice package to work with. And there's these similar FSAIL concepts in both Julia and R. You can mount S3 storage as a POSIX file system. I really don't recommend you do it unless you have a legacy application which has very modest I/O demands, like S3FS and rclone. Just that fuse abstraction really slows it down. JuiceFS actually puts a file system on top of S3, which performs really well. There, you can no longer use a native S3 tool to read and write to that data because JuiceFS has put the equivalent of a file system on it, but it's still very powerful. There's some really nice data version control tools which people are starting to use, especially in this generative AI space where tracking your data lifecycle and provenance is really important. You can use OSN with GitLFS. You can use it with DVC, which is data version control. It's another command line tool for versioning your data. Or LakeFS, which provides multiple APIs for reading and writing data on top of S3. So earlier today, someone asked about data warehousing. So LakeFS allows you to have interfaces to like Hive or Iceberg or Spark in the Apache ecosystem, and many other open source tools where you write their native API to the LakeFS middle layer and then use OSN in the backing store. And finally, multiple universities are using OSN as the backing store for their data management platforms. Delaware is putting into production a large 3 petabyte Dataverse solution. Caltech Libraries is using Invenio RDM, which is the open source version of the software which runs Zenodo, which is CERN's data management platform. And then Clouder is written and offered by NCSA, and iRods by our partners at RINC. And so how do you get started on OSN? Well, first, if you want one of our buckets throughout the nation, and you work within the NSF Access ecosystem, you can go to accessci.org today, request up to a 50 terabyte allocation, and get a bucket in a couple of days on one of our pods nationwide. We also have a pod in our data center, which is funded by OSN and the MOC team. And so it's our test pod, but you can get a bucket there to start experimenting with MOC and NERC resources that are backed by OSN storage. And finally, you can buy your own pod. If you're interested in buying your own pod or partially interested in purchasing part of a pod, I now have several projects who need more than 50 terabytes, but don't quite need the full 1.5 petabytes, who are interested in splitting partial pod purchases with other projects. Just reach out and let me know what I can do to help. And with that, I'll take any questions. There's one back there. Oh, okay.
On the requirement for access to large data sizes, like if I have a project where I actually want a bunch of, I don't need 50 terabytes of space, but instead I need like 50 gig buckets that are separate with different access policies. Is that still appropriate, or?
Yes.
Okay.
Yes, that's the way it works. So basically through Access, you would get a storage allocation up to 50 terabytes. And then that'll give you your max capacity or quota on the storage network. And then through the Coldfront portal, you can divide that into n number of buckets that sum up to 50 terabytes.
Okay, thank you.
Yeah. I have a lot of projects that I've worked with in a previous lifetime who were all IoT and air quality sensors, and they use that to aggregate small CSV files, right, that they then publish on a GitHub Pages website. So yeah, perfect use case. All right. Yes?
Could you go back one slide, just a second? So you had the hardware right there is $100,000 for 1.5 petabytes. That's $60, $66 per terabyte. And you said earlier that you could do it for 20.
That's for 5 years. So it's $100,000 for the hardware, right? And then $50,000 for the support, right? So that's $150,000 over 5 years.
Oh, and your earlier number of $20 per terabyte was per year.
Exactly.
For 5 years.
Yeah.
So it's 100 actually. So the hardware is costing $66, and you're charging.
The hardware
100.
buys you 1.5 petabytes of usable space, and in the graphs I said I did it per terabyte, right? So it's roughly, if you're buying a pod today, it's $80,000 for the hardware. Though that we expect that price to go up, and we can talk about it offline. But a pod today is $80,000, and then you send us $10,000 a year. So that's $130,000 over 5 years for 1.5 petabytes of usable space, which is less than $100 per terabyte per 5 years.
Which is the $20 per terabyte. Yeah, because so my question was going to be like, what is the fraction of the hardware versus the operations and the overhead? And so it sounds like it's something like 65-70% is the hardware, and then 35% of the operations. But you're not charging for personnel time because people are doing it on nights and weekends, volunteers.
The important asterisk there is our current policy is it's $10,000 per site per year, not $10,000 per pod per year. So if you buy 4 pods like AM&H, it's still $10,000 per year. The operations doesn't scale based on the number of pods you buy.
Yeah, and so just as an interesting data point, so when I was at EMC, we were building these systems to sell to customers, and then customers often we were often competing against the cloud. And our rule of thumb guess was that like AWS is about half the money they're spending on the equipment, and the other half they're spending on operations and networking and power and storage and whatever. So you're able to do better than that by, working for free.
Yes, by working for free, and they can't buy anything they want, right? I've generated a solution ID with Dell, and so you basically provide the solution ID, and it gives you one set of hardware, and thus the same set of playbooks work everywhere, right? So, and then reducing the feature set that we support, right? All right. Any other questions? All right. Thank you very much.
So actually, first of all, it's really cool to see where you guys have gotten to. I'm very excited about this. I guess a few things I'd just like to, over long term, we should get LSVD running on top of this now that you have that. And I guess two other things is one of them is that you have the location in some sense defined across all these pods. That's where you get the allocation, which is sort of consistent the way we talked about things is you get in sort of our vision of the open cloud, if you get an allocation in an area. But it also feels like we should be able to use this for caching things, right? So, if we take further what we've been doing with D4N and we talk about geo-replication, then you access it at the nearest access point. And this is going to take a long time to do, but I'd really love to start figuring out how we can do that. And then I guess my last question, and then I'll let you answer, is not that I really had questions, but is right now you're charging at this unit. Is there a value at some point for us to go sort of the consumption-based charging to end customers, like to integrate that model? How do the two relate?
Well, so John just walked in behind you, so if we're changing the cost model, you can talk to him. But no, I'm just kidding.
Walking into a room where Ron and Chris are having ideas is like a terrifying experience.
Yeah, we're planning your demise behind your back.
You can answer the question now.
So he was asking about OSN going more to a consumption model as opposed to a per appliance model.
Not moving to it, but just
just augmenting it, right?
Something.
I think all things are possible, as you know, but it's been really nice keeping it simple.
Yeah.
And simple hasn't been trivial.
Yeah, but to answer your question around the caching, yes, I think OSN and the type of technology that Spinning Disk and S3 provides, as well as the level of resilience, is the perfect backing store, right? And because it's over HTTP, you already have sort of Squid and those type of proxies, which can do a lot of the caching for you if you wanted to grow your own tool. And the D4N tools and along those lines are kind of what we need in this space, right? There are some very nice commercial solutions that sort of do this caching for you. And one of them that I've been playing with is called Versity, which was based on the fork of SAMQFS, which came out of Sun before Oracle bought it, where you basically have a POSIX layer, and on the back end, historically, it's tape. But now you can also do the back end with S3. And the performance, so they have NVMe drives and sort of a local POSIX cache with backing stores that are S3, and then eventually Glacier on the back end. Providing something like that and developing something like that around open source software would be an amazing addition to this space. All right. Thank you for, I'll come, I think it's time for lunch, or I don't want to hold people up. Okay, I'll come find you.
Chris. Okay, that concludes our morning program. We now have lunch, which will be sponsored by, our lunch is provided today by Lenovo and NVIDIA, so I'd like to make note of that, and please enjoy it, and be back here for 2 o'clock for our afternoon session. And all discussion leaders, could you just see Tara during the lunch break, please? for this session. We have governance and partnerships, fostering cloud adoption using a community-driven approach, Back to the Future systems research, and OPE and education on the NERC. So each of those four will have a representative speak about them for about 10 minutes. And then after that, we're going to have a member of each subject area. So the two from yesterday, AI Alliance and the Marriage of Data and Compute. And then this morning's Open Cloud group, and then those 4 sessions. And what we'll do is we'll have a leader from each of those groups meet, and we'll just have open discussion. You can choose which group of the 7 you want to go to, and then you can discuss, and then everyone will come back here, and we'll have a little bit of feedback on what went on and what we talked about and how it all went. Because I know some people have a little questions about what we're going to be doing this afternoon. So we wanted to have some open dialogue and talk about things that mean the most to you. So I hope you enjoy that part of our presentation, part of our program. So right now, let's kick it off. Who do we have coming back here? We have John Stump and John Goodhue with our governance. Thanks so much. Have a good day.
So I'm John Goodhue, the Executive Director of the Massachusetts Green High Performance Computing Center and friend of the MOC, maybe. Ron and Nancy and company had asked John Stumpf and I to talk about governance, and you can judge whether we actually did that after the end of the talk. I was struck maybe by 2 slides that have been recurring kind of in this conference. One of them is, I think Wayne called it a, I get to the right place, yeah, kind of what we've built, right? There's this stack of services that are production services, you know, MGHPCC, NESI, NERC, all playing together now. And then there's this ecosystem of people building new and adventuresome and crazy things, sometimes on top of that infrastructure, sometimes independently, with this intention to bring the good stuff into the production world. And then both a robust research community and a robust education and workforce community using the production services and maybe getting some visibility into the research. It's a big and interesting and complicated soup. Another kind of view into this, whoops. Oh man, there was another great slide, but you don't get to see it. But I can describe it, right? This circle that's starting to work, right? Of production services, fueling innovation, fueling industry engagement, and that feeding back into production services. It's a really compelling picture. It can sometimes be confusing about how to engage. And I think that's really where John and I converged, is not so much how do we govern, but how do we make it easy for new people in particular to engage with the MOC Alliance. It occurred to us that there are kind of 3 different stages of engagement. There's the how do I sign up, right? So if I'm at BU, maybe it's relatively more obvious to figure out how I sign up. If I'm at Framingham State College, maybe not so much. How do I pay? I think that's been the subject of any number of presentations today. And then what happens after I sign up, right? And you'll hear, I'll disagree with Nancy a little bit, some of the presentations in this session will elaborate on kinds of engagements after you've signed up. You know, the research visitation, support and systems research, classroom use, and maybe some other things. I'm realizing that the beauty of Google Docs is there's always like 8 versions of the presentation, so when I did the updates on the presentation, I did the wrong version. But these are kind of different ways to engage, different stages of engagement. And then kind of on the other side of the ledger, we have tools that make it easy. I think for a long time, engaging with the MOC or the MOC Alliance, your way in was you knew somebody, right? You knew Aran, you knew Milson, you knew Michael, or maybe you knew Mike Zink, and he was connected. And there was an easy way in once you knew the right person. As the MOC Alliance grows up and scales, it feels like they've done a wonderful job of introducing kind of tools and methods that make it more simpler to do the easy things. So if you go to the MOC Alliance website, starting yesterday, it's an entirely new picture. That's an interesting roadmap towards or showing the kinds of things that are now available just by going to the website and following the process, as opposed to knowing somebody, and doing something ad hoc. So it's not so much governments, but it's certainly kind of a growing up and scaling of how the MOC Alliance works. And I chickened out a little bit. I was going to try to navigate the website live, but I'll just do this picture. You'll see now there's a collection of things that are up and real. You can learn about who we are, and then with respect to services, what we do, and each one allows you to drill down how support works. Milson and company have developed an extensive user guide, so again, you don't need to know somebody, you can actually go read the manual. And a whole section on how costs and billing work. We've talked about questions about how money flows and so forth, but over the past year or so, the MOC Alliance has put together a really coherent way of how you compensate the Alliance for the value that they deliver. I will stop there. That's kind of a little view, I think, of where we have come, which is a really long way, and hand it off to John, there he is, to talk about questions about where we go next.
Thanks, John. So what I'm looking to do in our session, in our breakout session, is talk about the partner engagement. I'm interested in understanding, your experiences with the MOC Alliance. So the NERC has a fairly robust way of engagement. I'd like to apply that across all of MOC. And this is not only for researchers who want to come, but also for providers who want to bring their technologies and various capabilities to the MOC Alliance and expose them to the robust research community that we have. So what I'm trying to do is get us to become more efficient, where it's not word of mouth, it's not who you know. It's a more formal way of engaging and a more reliable way of engaging. I want to make sure that requests are satisfied on a timely basis. I want to note that any requests that can't be satisfied now, that someone's paying attention to that and seeing, are there ways that we can extend what MOC can do to address your needs? So what I'm asking for in our discussion is, one, feedback on your interactions to date, how you think they could improve, and ways that you would prefer to engage with us. Is documentation the better way, and just tell me how to do it and I'll figure it out, I'll read myself, or is there other ways that you would like to communicate? So, with John Goodhue's context of, how we've engaged in the past, I'm looking towards the future of how we might do this better and in a more formal way. And that's it. So please join us later today. Thanks.
Okay, so my name is Milson Munakami. I'm a lead cloud engineer at Harvard University Research Computing and Data Services, and primarily working on NERC, New England Research Cloud. And with me, I have Christopher Simon, Deputy Director of MGHBCC. So we're going to talk about fostering cloud adoption using a community-driven approach. So we, from yesterday and today, we reference NERC in many places. So what is NERC, right? So maybe some of you already using NERC on your research, some of you doesn't know what NERC offers. So we have different on-premise cloud computing services. For example, we have infrastructure as a platform, as a service based on Red Hat OpenStack. So here, user can request for dedicated virtual machines or VMs where they can use any root access. So they can install any kind of packages on them and then expose them to the public. And beside that, we also offer, based on Red Hat OpenShift, infrastructure as a code services, infrastructure as a service model where we allow user to have containerized workflows like Kubernetes and Dockers, right? And also recently we also launched this Red Hat OpenShift AI, which is more tailored toward the machine learning and AI and data science kind of platform. So here, user can customize their own images, upload their image as well, and then deploy them onto the different workbenches. And those workbenches can be shared among different researchers and their team. And also we have this storage as a service model where we offer different kind of storage options to the users based on NACI. So we have block storage that can be easily integrated or mounted to the virtual machines or the containers. And also we have more API-driven S3 compatible object storage, and that can be used on the applications using different programming languages as well as in different clients. So apart from this, we also offer facilitations and the consultations, right? So there is always a knowledge gap between the evolving cloud computing technologies and the academic professionals. So we want to bridge those gaps, so providing different user engagements and outreach programs. So why cloud? That's the question everybody wants to know about. Why not use the traditional HPC or HTC kind of setups? So because clouds give you more freedom and also more agility towards your research, right? So you can get more control over your resource and your environments. And this kind of interactive and on-demand compute can be very helpful for any scientific research. And we also incorporate different compute, like cloud-native computing environments based on Docker or any other new technologies like Kubernetes. So underneath, you're going to get all the benefits of those new technologies. And yesterday, we saw Dataverse can also be run on NERC. So those kind of data management portals can also be part of NERC, where the reproducibility can be easily achieved, right? So we saw the governments, we saw the provenance of data, applications, and the compute together. And then we can do all the reproducibility effort within the same environment. And beside that, we can also get more other benefits having cloud, like scalabilities, like you can do manual scaling or automatic scaling on the resource that you need based on your demand. And that is very helpful for any research. And also inbuilds more security features within the cloud can be very useful for data sharing and collaborations. So currently we have different kind of use cases on NERC, mainly web services and portal, so that research can share among the collaborators. They can share their data, their research, and then continue working on that, and future research can be done. Beside that, we have data and database servers that can be easily hosted on NERC. For example, we have one example where the researcher is trying to host whole human genomic data sets. So that's around 32 terabytes of data. So those kind of data can be very helpful and very can be a good asset, not just for one community, one particular research group, but for the whole scientific community. And yesterday we talked about data as a king, unless those data is available to the users. And those visibility can be only achieved when we can explore those data by using different kind of analytics tools. So NERC provides those kind of tools. For example, we have RSignees or Spark. Those kind of tools can be easily integrated within NERC. And those analytics tools can be very useful to understand about the underlying data sets. And this kind of non-HPC kind of workload can be easily loaded on cloud-native way on the NERC. So user can get not just CPU, GPU-based workload as well. And there are different kind of inbuilt pipelines. And also user can upload their own custom pipelines. For example, CI/CD pipelines, as well as machine learning pipelines and workflows can be easily integrated on NERC services. So currently, we are hosting different academic courses and classes, like Oren's class from BU. They are using Red Hat OpenShift AI. So many students can use the same workbench or share the same code base and then share the outcome to the class. So this kind of academic courses and class can be easily supported on NERC as well. So this gives the high-level stats about NERC. So you can see there are 11 different institutions, not just BU or Harvard is using NERC. And there are 771 total users, 67 different PIs, 121 different unique projects, and 41 unique field of science. So all these different field of science have their own research problems and their own use cases that is hosted on NERC. So recently, like John mentioned, we launched this new website. So if you can, go to nerc.mgspcc.org so you can understand what kind of services we offer and how to get it started with those services, and also know about our team and work. So we also listed different kind of use cases and projects that we are currently hosting. So next I call upon Chris, who's gonna talk about our current user engagement and outreach strategies, and also talk about the future direction for this one so that it will be more proactive.
Thank you, Milson. So as I mentioned earlier today, I wear multiple hats at the MGHPCC, and one of those is NERC Engagement Coordinator, trying to lower the barrier entry and really increase the adoption of our cloud resources. And as you can see here on the left side, we currently have a lot of activities, standard ticketing and documentation and things of that nature, but we need to build off more educational opportunities as well as sort of try to build a more self-supporting community. One of the nice things about bare metal HPC and batch systems is we have the established pedagogy and course material to onboard users. But the onus is really put on the user when you're working in the cloud to understand new concepts. And so we've identified a couple of short course topics that we think you guys would be interested in, and I have them listed here. And one of the things we're going to do in our discussion period today is go through these short course topics and talk about how these topics map to the capabilities that are provided by the cloud, and also solicit input on some other courses you think Milson and I could develop to really help improve your MOC and NERC experiences. On top of that, we'd really like your input on how we can build a better community. When we work in IT support, so much intellectual property and really good stuff gets lost in the back end of ticketing systems. And so ticketing systems are great for requesting access and requesting resources, but how do you do X, or when would I use Y, is things I'd really like to get out more in the open. So we've talked about a couple of different ways, like creating a Slack channel for users, maybe doing regularly scheduled Zoom-based office hours, setting up a NERC or cloud-specific online discussion forum, maybe leveraging the discourse-based Ask CI, or setting up something similar to like the Linux user group model or the old Usenet groups. And in particular, OpenShift AI through Red Hat, they also have a user group. Our goal is really to be more reactive than, to be more proactive than reactive. And so during our discussion period, which will be somewhere over here, we'd really like you to get your input on what are these tools you would like and how you think we can build more of a community. There's only so many of us on the user support side. There's only like 4 of us, and there's thousands of you guys, right? So we really want to build a community that builds up expertise together and has ways to sort of communicate what they're doing and sort of build a self-sustaining user group. So thank you very much, guys. And next up, I think we have Mike and Heidi.
Okay, we have 5 minutes to talk about all of systems research in MOC. It's impossible, so come look for us if you want to find out details, but we're going to give you a really high-level view. So we talked about all the kinds of infrastructure in many other talks. I'm just going to mention 2 that haven't come up very much. We have mobile infrastructure because we're interconnected to the Coliseum testbed, which is a very large mobile testbed, and it spans US and international sites. So if you're interested in anything with edge, anything with mobile, talk to us. We have that, and we're very interested in the cross connects between them. We also have a lot of specialized hardware, and it sits in the CODES lab. And we don't talk about that too much because it's not part of the production stuff, but if you're interested in RISC-V or ARM or special purpose things for factories, anything like that, please come talk to us. Okay, so this talk is about back to the future. That's because a lot of the systems research we've been doing for 5 years, we're still doing. And we started thinking about how it compares to the movies. So first of all, we're building systems instead of DeLoreans. These are bullet points of the things that we're doing that are important and continue to be important. So connecting all the eras of test beds. You've heard here several people who do test beds. They're hard to interconnect. We figure out how to do that. If you have new ones, we'd like to hear about it. We're starting to look at sustainability and power usage. So like the DeLorean, we have a limit on how much power we want to use. We also want to go faster than 88 miles an hour. So anything with high-speed networks, we have an interconnection to the Fabric network, which can go at 1.2 terabits. So we're really looking for ways to stress that. That's an exciting new thing. Whoops, sorry, I went too fast. Getting data and compute together, that's been mentioned multiple times. A particular area that we really would like to emphasize here is data privacy, because once you interconnect data and compute anywhere, if you don't take care of the privacy of the data that's there and the access to it, you're not going to have machine learning that's able to do very much interesting stuff. So that's a new area. Edge core I've mentioned, and software development. Basically, it's the Mr. Fusion of this whole thing. So if you're interested in software development, we'd love to have contributors. Please join us. And Mike's going to talk about 2 examples.
How many minutes do I have left? 2. Okay. In 2 minutes, I will tell you the rest of it. So,
that's more than you asked.
6 minutes. Okay, take a deep breath. So, that's fantastic. So, what I love about the MOC Alliance is this ecosystem we have, and I think that really is part of the systems research, because we're just not doing it. Where's Michael Datesman? He said professors in the ivory tower, right? Oran is like pushing us all. It has to be production, it has to work on the production. And so we're getting to this point where we come up with crazy ideas, can try them out in part of our test beds, but then get them in production. And we saw the CRISP project yesterday with this wonderful projects and work they're doing in the medical field and all this stuff. And I think where the potential of our systems research is really shown well through some of these examples here and all the different projects that are involved in that. And you probably know Oran is going a little bit faster than 88 miles per hour. So I always have a hard time keeping up. So if there's something not accurate on this slide and a little outdated, I apologize for that. So that's important. And I just want to give you one example because, you know, I've been really heavily involved in that in the Open Cloud testbed. We've been really heavy on deploying FPGAs and making them available to the research community. And I think that is something which hopefully in 2 or 3 years we stay here and say, we have this in production, right? You can go over to NERC and you can get an accelerator and do AI on FPGAs because it makes this thing so much better, that thing so much better. And I think that's what I think is really part of our systems research here is taking on new challenges, taking on new technologies, new ideas, and bringing them into a space where systems researchers can use them, but maybe further on, researchers from other domains and some further away applications can make use of them. So if you have some specific questions about that, please come and see me after the talk. So what's the real future, right? Our talk is back to the future, but what's into the future, right? And so one of the famous quotes from the movie is roads, we don't need roads, right? So I think what I would like everyone to think about in a moment is, or for a moment, or maybe this afternoon, what do we not need anymore in the future? Won't we have CPUs anymore at some point in time, right? Will it all be specialized accelerators? Won't we have buses anymore and everything will go over the network? These kind of things, right? So I think this is just, you know, Heidi and my thoughts on this, but I think as a community we can be, you're all much smarter than I am, so as a community we can come up with what do we need for the future. I think it's going to be more AI, at least for the next, I don't know, 10 years or something like this. Security has always been important, and I think there's been a lot of work happening under the MOC Alliance in this area already. Heidi put on sustainability, and we heard about sustainability a couple times already during this workshop, and I think that's important in terms of how do we look into carefully using resources for all the test beds, all the infrastructure we put in place, because I truly believe that we have to be a little bit more gentle to our planet than we have been in the past, and that's important. John and Jack, I didn't put on this quantum computing after I talked to you. Heidi can attest that I put this on a couple of days ago. So I think we're at the verge where hopefully we'll see quantum computers being able to really compute something in the future. And how do we tie this into systems, right? I don't see quantum computers just existing in isolation. They will be connected to our traditional compute systems, to networks and so on. Otherwise, they will not be of the broad use people are envisioning them. How can we have a role in that future? Probably most important is education and training, right? My joke is always, we want to retire at some point in time, right? And I'm going to be done in a second. We want to retire at some point in time, so we need to educate the young people here in the room to, you know, come up with wonderful, great ideas and do wonderful work. And, you know, thank God I could present with a woman, broadening participation, right? Making the room more diverse as our population is, I think, should be another goal for our future also. Thank you very much. Any questions? Oh, no discussion. Okay.
Thankfully, I just set my timer for an hour and 10 minutes, so I'm sure that'll be okay. Since, after all, I'm kind of known for my brevity. Great. So actually, at this point, I guess I'm more or less a figurehead here. We've reached a point. Oh, thank you. At this point, John had mentioned there's a very interesting loop that's formed at the MOC and NERC, and I think we're an example of that. And I'm sort of on the tail end and stepping out, and the real folks that are responsible for what you're about to hear about is really Danny, Isaiah, and Dylan, and Heidi, who have actually taken the next stage of showing that we can actually scale education on the MOC. The OPE project was actually just a harebrained way for me to try to get people to help me to scale the building of a the education of a low-level systems class on scalable resources in containers using open source materials so that we could demonstrate that actually real education can happen out of best-of-breed tools. But what we've ended up doing is evolving that further into, now at this point, we're going to present to you a little bit about an architecture that we evolved this idea of doing open source education out from just my class or the class that Aran was doing into an SDK and a toolkit that would allow people to get the construction of a container and textbook material, have some help with that. So that was one aspect that the project has evolved to. But then the second aspect that a lot of focus has gone on this year is to demonstrate that we don't need to use AWS. We can actually put this last layer that we were after, which is an open data center on an open cloud. Up until this year, everything we were doing was on AWS. But now we've actually reached the point that we have hundreds of students taking classes on the infrastructure in the NERC, and that's really been powerful for us. It gives us much more freedom and control. Okay, so I'm just going to briefly tell you a little bit about from the OPE, so this idea of how do we construct or encourage educational material being built in open source tooling, but not being toy. How can we actually build educational material that can let low-level systems classes to happen? So what we've evolved to is an idea of an SDK model. So this is kind of a big, complicated diagram, but the most important thing is that the Red Hat team has taken our sort of seed ideas and turned it into an SDK with a command line tool and a whole bunch of underlying repositories that allow you to very quickly bootstrap a new course, where a new course is composed of stuff to build textbooks, but these days also to build containers that contain all the software required to run your class, such that these containers can then be input to the NERC, for example. But also that it seeds you and encourages you that all the material you build ends up being repository controlled. So you can build a community around your class, and that has nothing really to do with OPE, right? In an open source way, we don't require lock-in. However, on the top half of this side of the diagram, we also encourage folks to help us build that SDK and evolve it. Okay, so now I'm going to hand it over to Danny to tell you about what's actually possible now on both of these fronts.
So the first thing possible is we are able to construct a course with books and containers. So OPE tools standardize and ease the construction of core elements of the materials. This includes not only just books such as textbooks, lab manuals, but also the environment where students engage with these materials, that is, containers. The process is quite straightforward. To construct a book, you can simply run the command OPE new book, and this will create a new Jupyter notebook for you. With the support from Jupyter Notebook ecosystems, authors are provided with templates and examples. They can now add and modify contents to their book. Once the contents is ready, OPE build command compiles all of the chapters and renders them into accessible formats such as HTML. Then the last step is OPE Pub. It makes your book published to the web via GitHub page. So now let's explore how an educator can construct his customized containers. You don't actually have to create a container from scratch. OPE tools have already prepared that for you. So you can simply run the command OPE new container to create a container. Then you can add course customized softwares, package, and dependencies in your container. OPE build command compiles all of the customizations, and you can now push the container to a registry such as KIO. Now it's time to deploy your container. You can either choose to deploy it on a cluster such as NERC OpenShift, or you can spin up locally. It's your choice. Authenticated students can now get access to their containers via web browser or run it locally. So yeah, here is a quick glimpse of the current CLI tool, the functionalities that it has. And if you would like to dive deeper into the CLI tool, we've already prepared the user guide for you to get started. So our next topic is OPE on NERC. Professor Apawu will share his insights into the success stories of courses using OPE on NERC.
Great, so the second aspect of what we focused on then is now independently, how do you, independent of OPE, how can you use the NERC to run your class? Now in Truth in Advertising, some of the folks who've been running the class this semester, since this is the first semester that it's been running on NERC, I was just chatting with them, and yeah, we've had some problems. As a matter of fact, we had a problem where our users, 150 students, because of a freedom in the front end, created usernames that didn't line up with their BUIDs, and for a bunch of time, students couldn't figure out why they couldn't log in. We had a problem where we had an outage. We had a problem where the staff was not able to use the same amount of storage as they were used to when we had configured it on AWS. So we are definitely running real things. And we are definitely on the path to doing this in a way where we've run those real things with 300, well, actually well over 300 students, and we're resolving the bugs. And if all we've had go wrong is one 12-hour period where we lost the system due to actually a fascinating bug, and then having user IDs unable to match up usernames, no one's complained that the container went away while they were writing their assignments. No one has complained that the system roughly all of a sudden froze. Have they complained about the course material? Of course, so that we must be doing the right thing. Okay, so in this last semester, we've been having our class 210, we've been having ECE, Introduction to Operating Systems, and we've also been having data science classes that don't use the OPE containers, but more broadly access the system. Yeah, I'm not going to pay attention to the sign. So the last thing I just want to really focus on is that the model that the student sees is simply, we're releasing students into a system, they get a container, and they've got a web browser. That's it. Now, Danny will actually tell you how it actually works.
Yeah. I want to highlight the core strengths that set OPE apart. That is, we have the flexibility and the ability to support customized needs. First, let's start with scalability. We've conducted tests on NERC Production Cloud before classes began to make sure that a surge in student accessing containers won't lead to significant delays, and the results were very promising. Initiating 300 notebooks concurrently led to an average latency about 20 seconds per notebook. More importantly, this testing framework is built to adapt to a range of OpenShift clusters, offering flexibilities over a variety of environments. And secondly, it's about cost efficiency. We have implemented a notebook shutdown cron job tailored to instructors' needs. This cron job runs every hour. It kills idle Jupyter notebooks after a preset time, and also remove containers with wrong image or wrong container size that students might have accidentally created them. This is aiming to optimize resource and reduce cost. We are also actively monitor and report our resource utilization to better understand usage patterns. So on the right side of the slide, the first graph shows the weekly resource utilization, and on the 6th day, it changed dramatically. That's the day we officially applied our cron job. And the second graph shows a daily resource utilization, following by the starting of the cron job. It offers a clear view of how the cron job help enhance the efficiency. So I also want to emphasize that these improvements go beyond just scalability or cost efficiency. It's more about making open education and research infrastructure more accessible, sustainable, and efficient. As we move forward, it's exciting to see potential courses and student projects are eager to use OpenShift AI on NERC. They are from data science projects to software engineering courses. With OpenShift AI on NERC, students and researchers can gain access to not only just Jupyter notebooks, but also a variety of advanced features such as AI, machine learning, model serving. So lastly, how do you contribute? So we have experienced students in helping us test and improve OPE. So please come to the discussion group to dive deeper. We also provided additional resources and talks on OPE for you to get started. Thank you, everyone.
One last thing. We were informed to tell you that the barn doors are open. We are encouraging and want classes, and we're ready to do it. So please come and chat with us and tell us about what you'd also like in terms of if you're planning classes.
So I'd like to add two things that weren't stated. First of all, the work was awesome, but it took 15, 20 minutes to spin up 100 machines on AWS last year, 100 containers, then 20 seconds is the average now. So that just shows the difference when you get bursts of students. And the other thing is that last year we calculated it was about $170 per student term for the kinds of courses we're offering, Jonathan and I, and we estimate the cost this year will be about $20 per student term. And it's now being charged by, like, so BU departments are now paying for it because it's sustainable at $20 per student, whereas 170 was not. So I just wanted to add those 2 points. And thank you for covering the bill last year, Heidi.
Okay, great. So now we would like to have a much more inclusive, collaborative, talking about the 7 subjects that we've discussed today. So each subject has a leader for you, and what you'll do is you'll pick one of the 7 groups to go to. You can have an hour discussion and talk about different topics that mean the most to you in that group, and the leader will come back and report back out as far as what you guys discussed and have some interactive collaborations among all of you. So if you, we're going to put the 4 topics that happened this afternoon. So governance and partnerships with John Stumpf and John Goodhue will be here in the front on the right-hand, or my right, so your left. And then we'll have Milson over here on the left in the front row. And then, Milson will be with the community-driven approach of the cloud adoption. And then we're going to have Michael Zink and Heidi with the systems, and they're going to be in the 2nd or 3rd row over here on the left. And then we'll have Jonathan and Danny over here on the right in the middle of the 2nd, 3rd row. Oh, the list is on the next. Oh, okay, I'm sorry. There you go. A little easy to look at. Okay, thanks. And then we're going to have the AI and the AI Alliance is going to be in the smaller ballroom, and that's with Sanjay. And we're going to have the Marriage of Data and Compute with Larry Rudolph in the back right-hand corner. And then finally, we will have the cloud, the open cloud with Christy over in the back left-hand corner. Okay, so they all have their signs. You can follow their signs like you did as school children to the bus and enjoy your talks and your discussions. Thank you.
And the big goal now, guys, is we really want this community to tell us and tell each other what we should be building. So come back and be very strong about what we're doing wrong and how this community should develop.
So I'm representing the AI and AI Alliance. We met out there, and we discussed a whole bunch of things. So it was a nice tour through some modern themes. So I'll just read them out. So we were first discussing compute. So there were autonomous cars like Eshed showed us yesterday in the 1990s. There was actually, I think, a self-driving car in the 80s from CMU called Albin. And the models when compute has driven a lot of the progress. The next thing we were discussing was the AI Alliance. What are the goals, especially given the very complex landscape of machine learning companies, so OpenAI, Anthropic, Google, and of course, Facebook is a big player. Another thing that's, I think, less well known, I just saw this paper last night, is now there are large language models that are quantized to 1 bit per weight. So originally, each weight would be an 8-byte float. There are different float formats, so people use something called a B float format from Google. But 1 bit per weight is shockingly low. There are also some interesting experiments where you can take gradients when you're training these models and treat them as ternaries, so +1, -1, or 0. And models still seem to train pretty well. We had one of the members outside who looked up the paper to see how much loss in accuracy you get. So for a popular data set called CFAR10, for a 8-byte float model, it was, I think, 75, 78%, something like that. For a 1-bit model, it went down to only about 65%. If you had just asked me how much do you think it goes down to, I would have said, I don't know, 1%, 0.1%. And of course, this is not well understood. But these are very interesting phenomena, and they have huge implications for energy consumption, for inference latencies. So that was one thing we discussed quite a bit. And related to that, there's a question of power consumption and training. GPUs are very convenient, they have high throughput, but they are very energy inefficient. And like Jonathan always says, there are old HPC architectures that are extremely successful and very energy efficient compared to GPUs. So the question is, if more and more organizations are going to train large language models, should we be moving away to other known computer architectures? So I think these were the main highlights from the AI discussion. Any questions? Oh. That's okay. Otherwise, who's next, Nancy? Larry Rudolph. Where's Larry?
Open Cloud was, who's Open Cloud? Yeah, John, jump up, why don't you come up in public governance?
Am I good? Okay. Okay. So didn't get any feedback. However, I did meet with someone who had questions about using MOC resources for essentially what are social science projects. It was a board member of the Urban League in Boston, and they are interested in using MOC resources for their coding and for their data. And there were a number of things that he hadn't thought about that MOC can bring in terms of introduction. So for all of their public data, the Dataverse represents a very capable location for their data sets, both for their raw data and for their analysis. They work with Code for Boston, and that would be a source for data analysts creating the skills necessary to perform that function, but then serving as resources. And then the member universities of MOC Alliance can actually provide social scientists, people who, master candidates, maybe PhD candidates, who would use the questions that the Urban League is asking as their thesis topics. So anyway, it was a nice meeting, and but if any of you do have feedback how to interact with MOC Alliance, still open, jstumpf@bu.edu. Thank you.
Larry, you're up.
We just had a small talk, Rory, Mark, and myself, and I found another marriage. That's between the physical and the virtual, or the physical and the digital, because research space is all about these notebooks and how to sort of organize your research project and the support for it, and that has a lot to do with samples and doing stuff. Writing things in your notebook, but you no longer write into a research notebook, you're typing and you're having links to lots of things. But you may be running an experiment looking for mutations and having Illumina sort of sequence stuff and the like. Many things that you do in the physical now space has a correspondence of doing something also in the digital space, or uploading data to NERC, for example, the simple thing. So the idea is, the simple, easy, actionable idea is when you upload something to something gets uploaded to the storage, have a trigger that runs some script, which then talks to your notebook and says, oh, this is the data we just uploaded. Rather than, I think, how people normally do it now is by date and month and year, that's their index. No, you want to sort of put it right into which notebook it is. When you get a sample arrived and someone pays the bill, you can sort of tie together all these streams together, both the virtual and the physical. And I think there's some immediate actionable item is just how these triggers put in. I think that was the main point. Anything else to add? Okay. Oh, that was a lot, and most of the people have left. Adam is very excited. Adam Belay is very excited about the connection between his traces and Memento. There's been a lot of discussions about Memento at different levels, and it's clearly going to be an action item. I think we have to sort of write up a list and get all the interested parties and get together. I don't think this organization is exactly the right thing, but man, everybody talked about it. It was sort of the undercurrent theme, as far as I'm concerned, that came out of this 2 days.
Actually, just really, I apologize, I should have asked this again. Sanjay, do you have anything to summarize, not just about the discussion here, but about that whole session? Sorry, I really wanted to say this again, I forgot, is that when you're talking, I want you to not just summarize what the discussion, but also just the whole session that you had. Is there anything else, or what interactions here that, from an AI perspective? Do you think we're doing something friggin' useful here, in some sense, of the MOC Alliance, of delivering things for AI? What are we broken? What do we need to do? Or are we on a good trajectory?
GPUs. Maybe we need more GPUs. I think many people would love to do larger scale experiments, training, fine tuning, like this 1-bit idea that was published. And the major bottleneck today is just getting access to GPUs. I don't think storage is going to be a bottleneck. That's cheap and easy. There might be more. I just can't think of anything right now.
So I'm going to just comment on that. So I just had, it was really interesting, Dave Paulides, I don't know if he's still here, but he was talking about in 2 Sigma, I don't think it was, well, tell me if I should shut up, but he was talking about they have these GPUs and they're streaming large amounts of data, and it's actually the GPU turns out that it's actually I/O bottlenecked of getting these huge data sets, and the GPU sitting there idle because they can't feed the darn thing, because if it's streaming through these huge data sets. So sorry, is that not the opposite of what you just said?
I don't know. So the fact is, we have never actually done these experiments. I know IBM has trained large models on OpenShift AI, but we have very limited experience training large models. So that sounds very reasonable, but I mean, right now we don't even have the GPUs. We haven't even started anything.
All right, then come get a microphone for it.
Yeah, sorry. I just was saying, you know, the difference is where the data is coming. Is it coming from some S3 bucket into segregated storage far away and then has to be deserialized and, you know, all that overhead to get it into the GPU, or is it already sitting on an SSD next to the big server or not, right? And that's a big difference.
As an example for what we're doing in the NERC now, we've generated all our data on the node, a few, like 13 terabytes, sitting off of the NESI attached storage, and we're caching it onto the node. So look, sure, in the large, and probably for 2 sigma, it matters a lot about that latency, but I have my data. We need GPUs to train the model on, right?
So this is my general thing I'm really curious about, is that I thought other people would know what the heck they were doing, you know, in terms of feeding the GPUs, like, 'cause we haven't had access to them till very recently, and they're almost up, right? But you know, how do we feed them? Like, what infrastructure? How can you, like, can they be to what degree is multiplexing possible, or is the 80 gigabytes or whatever of internal memory sufficient so that that's all you friggin' need? And it's like I've been asking those questions, and I don't know if it's just I'm too stupid, but nobody's been able to tell me this, which is.
So people don't know, and one of the reasons they don't know is because it is ultimately application dependent, right? So some applications are going to need more memory, some applications are going to need less memory, but
we should know the averages. We should know, like, isn't anybody monitoring a cloud environment and telling me? Like, you know, I had this conversation with Wayne, some researcher, though may nameless. I was asking them, what's their utilization of GPUs? And they said that they were 100% used, and then, what was it, 20, 15%? Yeah. So it's just,
and all I can tell you, people have been asking me to sell them GPUs for 4 years, and when I ask them what they want to do with them, 1 in 10 has an answer, right? And I can't sell them a solution unless I know what they want to do, because I don't know what bandwidth do you need, what storage, how much local memory, how much the thing. So I think the thing that David said yesterday, on, you know, some kind of benchmarking and some kind of comparison, you know, fidelity of the model, big model, small model, big GPU. So I think it's not known. It's not that they're not telling you, they just don't know.
Well, this is like when something's so expensive. I mean, even the cheap things we have in operating systems, we measure the bejesus out of them and we know how to use the thing, right? I mean, so is one of the biggest things, I'm asking this question, is one of the biggest things we can do is actually collect the telemetry and the information in order to be able to give these answers? Like, you know, where's Heidi? Oh, there she is. I mean, Heidi, like, I just, like, is this a value that Red Hat needs for its platforms and 2 Sigma? I just don't, like, do we need to build this, or do you, like, the telemetry? No, we don't need to build it. Oh, good. So what's the answer?
Well, I just comment again, it depends very interestingly in the usage model, right? Like, I actually do think there's some room for some telemetry here, but remember, for many people, if you've got your data close to you on your node or you're generating your data, as far as I'm concerned, yeah, to be honest, of course the GPU's largely underutilized while I'm interacting and just sort of sorting myself out. And then I might kick off a big batch train, and then it's going to be idle as I sort of play around with test inferences and do all that kind of stuff, because it's an interactive process for a while until it turns batch. Now, what we've noticed, so I have been, while we do it because I'm a systems guy, I have been running the NVIDIA tools to be keeping in the background monitoring both the memory usage and the power usage of it. So if more broadly that were sort of being measured and gathered and archived, yeah, I think as a systems person, I could use that. But I don't, but I think to the point that do you think your user knows that? They've never been asked to think about it unless you've been doing it at scale, in which you go, yeah, that's a different.
So let me ask you AI guys another question that I'm really curious. So another thing that David said to me was that a whole bunch of your use on Google's cloud or whatever, you're actually using spot markets. And I said, oh, really? There's a spot market for GPUs? He says, no, we can't. We do a lot of our stuff not actually using the GPUs, but just using the CPUs for AI. So, and all these libraries work equally well on GPU or CPU. Not equally well. I meant they work, right? Can we shift from using GPU for some period of time then not using a GPU, or do we have to, like, is it just frozen? If it starts using a GPU, it's stuck on the GPU. Like, can I multiplex these to accelerate them? I'm just trying to figure out how we can provide service to people.
So let me just talk real quickly about what you got and what you can get. Let me talk about the configuration of the node that you have, the nodes that you have, and then you can, and I'll tell you about the capability of it. So in the nodes you have are 4-way NV-linked A100s. So they can aggregate the RAM of all 4 of the A100s, and so you can load a model up to, they're 40 gig A100, so they're 160 gig, and run it across all those. The other thing that you have is a tool NVIDIA has called MIG, which is multi-instance GPU. Right, so you can cut them up to 7 smaller GPUs and cut the RAM up the same way. It happens to be in 7 equal slices. But from a management standpoint, from a cloud standpoint, you could sell all those instances or allow users to use all those instances as long as they fit within those, 1/7 of the RAM. So, I mean, you guys know about this.
Sorry, this is just me still asking dumb questions because I don't understand. Like, so I think that when I asked you or somebody else about this a while back, it was like the application specifies what they need from the GPU in terms of the memory. So if I can present a 7th of the GPU, it's not like it'll run slower, but be able to use it. It either fits or doesn't fit for the allocation, not the actual usage, right? Yeah. So, and how do brilliant people figure out how much memory they need?
So the thing is, most people who are actually building a model, you have no idea how big of a model you need for a certain task. So if you give me some, let's say, vision data set, images and let's say classification, something straightforward, I don't know how many layers I need. I don't know how big those layers need to be, right? So to be very precise, if they're convolutional layers, I don't know how many filters I need. If they're transformers, I don't know what the sizes of my keys, values, and queries should be. So I might experiment a bit. When I experiment, I might do it on the GPU or on the CPU, because I just want to make sure the operations I'm defining are working. I can flow data through my neural net. Then I might train. I might go and look at my test accuracy, let's say. Say, okay, it's good, it's increasing. Let me try increasing my model size. Maybe by doubling everything, I'm making my numbers up, but if I double all the sizes in my neural net, that means
that's always what we do, is you double it.
Not necessarily, but you increase it. Let's see what happens to my test performance. So I can't start by saying I want a test accuracy of, let's say, 95%. And from that, I cannot back calculate how big of a network I need. Now, there are some with LLMs, there are these so-called scaling laws, empirical rules or plots that tell you, well, if you have so much compute, so much data, and so many parameters in your model, your test loss or test performance should get to this point. But generally, for most problems, you don't know that. So if you give me a large GPU, I might not use all of it. Again, it depends on my problem and how much data I have.
Yeah, I think what you're saying is your problem is that you don't have it, you don't know because you don't have it. you don't have any access, so you have no idea how big the model is. There are some rules of thumb that you can use on number of nodes that create, model size, parameters, create equal, and NVIDIA can estimate that for you.
Yeah.
So
No, exactly, yeah. So even the scaling laws, you know how many parameters you roughly need, but they have those scaling laws because they took a lot of OpenAI's training data and literally plotted test performance versus number of parameters. But if you're starting from scratch on a new task, like the one that Jonathan and I are working on, is not text data, it's like memory traces.
Yep.
You have no idea, so you just have to do experiments.
Yeah. So I think the point thing here is just having access, Oran, and as time goes on, people will finite tune down to what they need, but right now they just don't even know because you can't get your hands on one.
Exactly.
Well, sorry, maybe I'm missing something here, but if I understand how it works right now is that a person specifies an allocation, and if they are trying to tune, they'll start off with the wrong thing and it won't work or something. But the thing is, given that unless I partition with MIG, which they'll go and they'll have access to the whole thing, right? And they won't necessarily have an incentive or knowledge that they can use something smaller, or I'll know that we should partition these a certain amount. I'm trying to figure out how we build a system, just to state this bluntly, is that our incentive is not to maximize the sale of GPUs. Our incentive is to maximize the use of the infrastructure and maximize the amount of science done on the thing. And I'm sort of frustrated from a bunch of the conversations over the last while on trying to figure out how to deploy this stuff, how to integrate into OpenShift AI and how to integrate into OpenShift. It's not clear to me how we should be both characterizing this, having the system, what telemetry we should be collecting, scheduling the system, and then there's another aspect, is how we should be building the system so that we optimize the utilization of the infrastructure. I think this is just a very big, I've asked folks, I thought IBM Research would have figured more of this out, but my conversation with them is, yeah, that's a really good question. And I'm eager to actually have folks focus on that here, or use the information we collect. Because I don't think it's the end users. The end users might be able to give you one data point, which is, I need less or I need more, right? But they're not going to be able to tell us the mix of capabilities we should provide, how we should bill for them to optimize the utilization, and even how we can context switch them. And actually, going back to the question, I don't think you answered it, is can, these tools, these libraries, can use either CPUs or GPUs. Can I switch between them? Can I just...
Yes, yeah.
Okay, so I can actually take away the GPU for some period of time and then...
No, he didn't say you can switch. He said he can switch. He can, in his code, go, I'm going to move to the GPU, I can move to the CPU. Right now, it's driven by the application's choice, not some layer below the application.
Yeah, you make the explicit choice. You say, do I want my model on the GPU or CPU? Do I want...
No, see, I want to be able to say, see, GPUs are contented right now, let me give the user feedback, or the library feedback, or OpenShift feedback, and have it switch to using CPU if GPUs aren't available.
So Aran, I think you're on the right track, but back up a little.
That's unusual.
So we can build virtualization layers to exploit that fact. But first, before you go there, I think you actually already have started to implement what is currently a viable approach to the problem, the pricing model. So why did I choose to allocate 3 of your nodes? I chose one node called CPU. I called another node GPU because I knew its cost model. And now I'm trying to use the one node to figure out when I've reached a non-interactive point that it's worthwhile me going and doing batch work on the GPU node. And if the VM allocation had been that I wasn't paying for that one while I was doing the exploration, I actually would have been forcing myself to recognize in my workflow when I was non-interactive and interactive. Now, a better model to that is to start gathering telemetry data and to start then figuring out, can we start to help identify these things and then potentially move them around? But I think these are iterative processes to get there.
Yeah, so, all right, I just first wanted to, I mean, part of my goal of this, of bugging you all with this is I was trying to understand if this really is an important problem that isn't, you know, I never, if Jonathan says, yeah, you've just done the right thing by exposing to me the information, I don't think most people are Jonathan. So it's actually, yeah, well, you get that. We can do that today. So yeah, no, I think I think that this is a really important question for us to focus on, and I think this is probably an important question for Red Hat in the platforms, and maybe even for Two Sigma and other companies, to understand how this should be presented and billed for, and et cetera. Okay, so John, when are we getting more GPUs? No, but seriously, do you have other things you want to say outside of the summary of the conversation? Okay. All right. Sorry, next group.
Let's move on to
apologize.
Christy in the open cloud. Michael in the open cloud.
I'm actually going up there.
Michael did homework.
Artwork.
Artwork.
And I didn't do it. Okay. So I should note, Christy delegated this to me. We wrote you a haiku. Open standards free, facilitation is key, quantum play we need. And because we had ChatGPT do that, we actually had to fix it because it initially gave us a second line that had 8 syllables. This is what we fed ChatGPT. Basically, open standard interfaces are a great enabler. They allow people to move workloads. But facilitation is at least as important as that. And we can't write the drivers for the quantum computers if you don't get us some to play. You could tell our table had a lot of engineers at it. And then we said to Dolly, make us some artwork. So this is what Dolly came up with. We had to give it a couple of tries to get it to do the right thing. I think I had a 4th slide. Did I? Nope. Oh, I did. And for the summary that Oran was asking, I can take this off. I'm up here. The session summary of what Christy talked about earlier is essentially we finally have all the building blocks, which is something that we've been working towards for a long time. So that's it. Questions?
So I was disappointed by that group because it was all the open cloud people sitting together. And you guys asserting we have the right building blocks is not confidence building for me. I kind of wanted other people saying that wanted to deploy services saying, yeah, you guys all have the right building blocks.
We did too.
But yeah, no, I'm excited that I'm excited that we have a set of building blocks sufficient to start with. I'm not at all convinced that we don't have to have richer telemetry, especially that's feeding this stuff, that we don't have to science on how we're going to properly bill for stuff to maximize the utilization of the value we're providing. But I firmly agree. It's exciting to have a building block sufficient to allow this to grow in a self-sustained way. So thank you, guys. In fact, I guess one thing that was bizarre to me is I wasn't aware of a set of the things that had been built, like some of the stuff that Hakan talked about. You know, that now we can actually get this whole topology and we can expose that, because that, like, if the Open Cloud Testbed has that topology, then it knows there's a source of truth that all the different things can use. Because right now we didn't have that, and we've been making it up. So, I'm excited about a bunch of stuff that was built that I didn't even know about. So nice job, guys.
Heidi, do you and Mike want to take on? Well, let us know what you discussed. Mike's going to do it?
I want a DeLorean.
Thank you. So we had a very lively group. We also decided that we need more GPUs, right? So that's a theme here, I guess. No, I'm kidding. I'm kidding. To analyze all the data we want to collect. Really, really good group. Lots of people together. Interesting discussion. My feat of the day was that Eric, Thorsten, and I were sitting together in the end talking German. Next time we'll do this over a beer. But coming back to the topic, systems research, Jack, who unfortunately had to leave, was talking about federation, right? So really we have all these enclaves maybe, right? And so how can we federate them together to do bigger things and not have people, you know, using 5,000 logins? How do we get them privileges, non-privileges, all these kind of things? So that's really important topic to think about of the future. We didn't talk really much about hardware. We talked about principles and how we analyze and support systems research. The analysis, data analysis, so first of all, capturing data and analyzing data was another big topic. Needing standards, needing units. It's not always time series. Sometimes, John mentioned scatter plots and other other approaches to really understand the data you're collecting well and learn lessons from that, doing your analysis and so on. And how does this flow with modeling, right? So what we saw is, and maybe that's, you know, I would really like feedback from everyone else, is also here in this group, we're a lot of systems people, but we don't have core modelers. And I apologize if I'm not ignoring someone. I don't do this on purpose, but it would be really interesting to get people who work on the model performance evaluation side together with us, because I think there would be a really nice interaction of, we have actual data, we can say how this is matched with models. We're just talking about predictions on GPU usage and all this stuff. Are there any models for that? Right? Have people thought about this? How does it match up? Well, you know, people say, you know, people have done, in the networking side, people have created models, control theory models for TCP, for example, right? Do they really reflect TCP, right? You measure it and you show it is or it doesn't. It does or it doesn't, right? So I think that's kind of what I mean by models. Large scale versus small scale, right? Some people say, well, we want small scale because we don't want all this noise that you get when you have a large scale testbed. Other people say, Roger had a really interesting argument. He says, I want large scale, I want to put proxies in so I can turn knobs and make increased delays, reduce bandwidth, do whatever kind of crazy things, and then see what that does with the performance of a large scale system like NERC, right? So that's another point. It's a little bit problematic, could be problematic, because what is if I'm the user and he throttles my bandwidth or something else, right? So we don't talk about it. Okay, that's a good approach. Coming back to the data, it's also sharing data, right? We need standards, how and what's it called, provenance, if we want to share data, so others can use the data in easy fashion. Oh yeah, I think Heidi had a great idea. And I pushed this even a little bit further. You said in the olden days, people would come together and bring their routers and do interrupt testing, right? And if you want to test federation and maybe other interoperability between test beds, why don't we do this? Why doesn't everyone bring their test bed in a box or something like this? And we have, what do we have? An interop test, right? I'm not allowed to say hackathon, actually. Oh, I did just say it. So some kind of event where people come together and test that. And I thought this is where ESI could be super cool, because we take, I don't know, I'm just saying it for the sake of argument, we take 100 servers out of NERC, ESI, 10 go to Cloud Lab, 10 go to Chameleon, 10 go to Fabric, 10 go to NERC and whatever, and we do interrupt testing, right? Perfect, right? So we could, maybe perfect, but we could do some nice side on that stuff. So that's a thought I really like, because you could bring communities together for federation testing and things like that. Am I missing something important? Okay, good, thank you. Or any questions?
I'm just going to jump in. In all seriousness, if anyone, just send me a paragraph or two. Tell me why you need GPUs. I'm serious. Tell me why you're hindered today. Tell me what you're going to do if I give you a ton of GPUs and what benefit it brings, okay? If you give me that, because I am working on trying to acquire 192 GPUs, okay? And help me get them for you.
Tala, you're writing this paragraph? Okay, thank you. My student.
Okay, Milson and
Just remember, it's not binding. We won't force you to actually do what you say. We just want good justifications. So while we're on this, one thing that came up today with talking to one of the folks is they were saying, we could get people to opt in to providing their data for systems research and stuff. And I guess that one of the, at least my beliefs, and I'm curious Wayne's perspective on this, is that I think we can be kind of pretty, like, we have to preserve student confidentiality. We have certain things we have to do to respect privacy, but in a sense, I don't think there's a problem in terms of making things, putting in a user level agreement to say, your data will be collected for research purposes. And your information about how you use the computers and what you're doing, not that we'll have file names, not that everything won't be anonymized, but I don't think we need to have people opt in. I think that if they're using, MOC Alliance NERC, they are not just users, but they're also subjects of study. Is there any problem in that from your perspective outside of whatever telemetry doesn't end up crippling the performance of the system?
I think a lot of it depends on where you live and what country you're in. And so, Europe has a lot more restrictions than we do.
No, it doesn't depend on that. Because what we heard from the lawyers, as long as they assert that the regulations don't apply to them, even if they're lying, it's fine.
The hand waving that Michael just did is probably what concerns me around that. So, yeah. So I think generally telemetry is valuable, and being able to provide that in a very de-identified, anonymized way for research, I think is a great idea. I think a lot of it has to do with compliance, and the compliance landscape is constantly changing, and we're having a hard enough time just on the enterprise side keeping track of it, or the research administration side keeping track of it, and having your research comply to it. So just saying, yeah, we should just do it no matter what, I think is a big reach, and we just need to tread carefully because the landscape will continue to change.
Okay, thanks.
All right. So Milson and I were tasked with the user outreach and facilitation discussions, and he and I made up 2/3 of our team, which really wasn't surprising, right? Because most of our target audience aren't here today, right? One of our jobs is to help people with what we call facilitation, and Oron suggested I talk a little bit about facilitation and what our potential end users might find frustrating. And so I find our job is kind of like computational lubricant, right? Or to talk to the end users and talk science, and then take those requirements and convert them to IT needs. Most of the people who are here who are doing science on the system are mostly systems researchers, right? And you guys are willing to learn the APIs and learn how to use OpenStack and OpenShift. But sort of the commodity scientist who might consume our resources is they have problems looking for solutions, not problems looking for Legos to build solutions. And so with you guys in the room who are people developing solutions looking for problems, the facilitation actually happens in the reverse direction. So, as you're developing something, I would encourage you to reach out to Milson and myself to talk about what you're developing so we can help figure out what science use cases they map to. And so when we're thinking about building out shared services, we really need to think about, the person doing, computational biology, genomics, or CFD, and they're not going to want to build something. They're going to want to consume something. And when you look across our member universities and look at what cloud services are popular today, it's not EC2 and load balancers and elastic IPs. It's Parallel Cluster, right? It's SageMaker, it's Google Colab, and it's simple storage services, right? S3. And we definitely have the components to build those solutions. In that regard, one of the things that I'm really excited about is OpenShift AI, right? I think OpenShift AI provides a lot of the capabilities that they get on these commercial platform but also sort of, puts our best foot forward, right? Our most compelling use case, in addition to GPUs, right, and real-time access to GPUs, is this kind of fuzzy metric, which I go back to, which is science per dollar, right? And that's really the big use case here is we can do the same things cheaper, but we need those shared services first. So Milson and I have been talking a lot about sort of education and short courses to try to help users come over that divide when going from traditional research computing systems to cloud computing, right? Most cases where people are first exposed to research computing is either their laptop or desktop, but it's probably their bare metal HPC system provided by their campus. And there they learn interactive, procedural, stateful batch workloads, right? And if we just give them a box of Legos, we're asking them to go from that to declarative, stateless, right, containerized applications. And so we've developed a list of courses and topics where we want to introduce those topics to our scientists, and we do think some domains would benefit by being exposed to, Terraform or Ansible or some of these, declarative automation tools. But at the end of the day, the vast majority of our potential end users are looking for solutions, right? And so as you develop things, please reach out to Milson and I, because we definitely have the most contact with new potential users who want to be onboarded to MOC and NERC resources. Thank you. Comments, Oran?
I guess there's a couple of things that, I mean, just in talking to sort of industry partners, I had several conversations with some folks actually at Red Hat, and they said, well, this is really cool what you're talking about, these sounds, can you come to KubeCon? And I said, nope. And they said, can you, will you kind of participate in open source kind of community to work on these things? I said, no. There's this separation of, as a faculty member, as a faculty member, I won't do that. I'm trying to do my systems research. Faculty members are trying to get papers, their students want to graduate and they want to get their papers. In a way, the same thing you're talking about of people just wanting to get their shit done. We have, so we can have needs and problems and even solutions and stuff, but we don't necessarily want to create that sort, but it's not necessarily, we're not remunerated to work to iterate on a patch with an upstream community until that upstream community has that. I think that what we do have is kind of partnership with Red Hat, and we'd like it to be a partnership with other companies that can come and work with you guys, I think, to hear the problems that people are having. They can iterate with us as systems researchers to kind of develop, at least in our case, prototype solutions to certain things. And we also have a team of engineers here who actually can work on helping transition when there's a community in upstream. I think this is one of the, I think the facility is, like you said, is lubricant, but not just for the users of IT, but actually in that whole cycle. And I think we've done something very unique with the Red Hat Collaboratory, where, especially with what Heidi's put in place around this stuff, that's enabled a richer interaction. But this is where I guess my head is. I think you guys can bring more of the problems. I think we can offer you to state the problems, but also you understand the resources we have in terms of engineers and in terms of systems researchers and the kinds of systems research that goes on to help identify the problems. Maybe, we have hammers and we want nails. So part of the things we can come to you and say, yeah, we have this hammer, do you have a nail? But it's also, I think, I'd like you guys to expose more to us what the nails are. Mm-hmm. Hopefully motivate us to do research to invent hammers for those nails, and then kind of closing the loop with industry and saying, hey, not only do I have this problem, but here I have this cool solution that's a prototype, trying to figure out how we build a process to actually get things accepted.
Yeah, definitely. And what I will say is also, as the solution builders, leverage Milson and I, right? Tell me about the solution you're building, and I can tell you what science use cases that could potentially map to. I'm a computational chemist by training, but for 20 years I worked as a hired gun while I was faculty in many different areas. So I speak almost every science domain that has popular open source software. So if you have someone who has a science problem and you're not able to connect to them and convert those to requirements, bring me into the loop. I'm happy to talk to them and take their needs and convert those to Kubernetes, OpenStack, storage, whatever requirements. That's where we're there to help, right? Both directions, not only helping the users figure out how to use it, but helping the solution builders figure out what needs to be built to help our users. Thank you.
Okay. Now we can finish up with Jonathan and Danny, please.
You hand it over like a knife, right?
So Danny, did we decide that you'd give the quick overview of how the discussion went?
Yep, okay.
Here you go.
Oh, okay. So in our discussion group, we have people there from Johnson's class. They are TAs from CS210, and they were sharing about their experience helping students figure out how to ramp up using Jupyter containers and help students register and debug their username issues, things like that. And we also have Red Hat engineer from OpenShift. He's working on education. He's very interested in our OPE use case. So we have some feature requests from professors and TAs, such as we want to improve our debugging experience in containers. We want to have more concrete error message when students facing problems when they are launching their container Jupyter notebooks. That's one thing. And we also illustrate some issues we are having with our current class. Our class on the Jupyter notebooks, that is all the classes are sharing the same namespace, that is default namespace, Rose notebook. This is really hard for accounting for classes for billing purpose. So that's the other issue. And Johnson also wants to have SSH ports for his class to directly use their local VS Code to connect to the remote containers. The other issue that are required by OS courses is virtualization. They want to have full access to OS stack in order to have to let students have full experience of kernel. Other than that, I think overall feedbacks are very positive. And no students are complaining about why their container is not working and not running, why their works disappears. So, yeah, any add-on?
Yeah, the only one I would add to that is something that came out of it was the consistency of the environment. So containerization is really helpful because it says that the bits that we're presenting to a student is stable from student to student, course to course, or sorry, semester to semester. But the other thing is the behavior of the container being consistent. So for instance, the TFs from my class pointed out that, yeah, it's super important that we had configured the instance of OpenShift to turn off address space randomization, because we actually present material where they have to, in a discussion, look at virtual memory addresses. We had to go through the process of understanding on the given OpenShift deployment which of these features were critical to the user experience. And so further automating that, and also the question of what that means then every time we do an upgrade to OpenShift, right? Because that's going to imply understanding good mechanisms for any given course's requirement for consistency. And then, at least I was very excited to find out that the virtualization support is already in the product, and that for at least my class, it's a simple, when we upgrade, I'll be able to try it out. So I guess the big thing that we really wanted to do, of course, was have faculty here to sell them on using it, but we'll have to do that separately, I guess.
Wow. Is that it? Iran? Then why don't we set up with your closing remarks, Iran?
I don't know about the rest of you, but I'm exhausted. So, first of all, I'd like to go back. It's like, as it says up in letters on the thing, is we finally have the building blocks. I'm just, thank you, Christy. It's just like, it's perfect. It's up there. This is really first workshop where I think we really do have the building blocks to where we actually, I don't know how much money we have in the bank right now, but we sent out our first bills. And I don't know why Jonathan didn't get his. He probably just hasn't read his email yet. But we actually have revenue coming in, charging for the computers or the use of the NERC environment. There's a lot of holes in it. It's like, I don't like the fact I built the revenue model, but even so, we did it at the NERC level because that was a clear thing. I'd like to have it at the ESI level to the NERC level. Each layer should be charged for. We have to now build the right infrastructure to meter it at the Lenovo level and actually send the right charges to there. But I think economics is fundamental to a cloud, building an economic model for charging, and that's been an adventure in a university environment to do this in a way that I don't go to jail, which has really been, which I think we've now had. And Wayne and
He's setting me up.
and Nancy and John Goodhue, thank you, because I know that was an incredible amount of work, and you guys had to deal with the lawyers and not me, so thank you. I'm very excited about sort of each of those pieces that came in place, and I'm also extremely excited that we now are finally collecting the telemetry that we've been sort of promising since the day the project started. So these components are really coming together now. That's incredibly cool. And parts I didn't even know about, like that we actually now have something that can collect the entire inventory of machines and how things are networked together so that as a user or as a platform on top of the base thing, you can actually do a mapping and say, oh, this node is next to this node. This is the allocation I want in order to do the thing I'm trying to build. So the AI parts I still am very confused about, but that's probably because we're only in our inception of doing it. I think the use case is important, and I'm just worried. I mean, John, you gotta get some GPUs, but I don't know if anybody's mentioned that. But I think that those components are kind of coming in place, and I think the AI Alliance is a really neat use case. And one thing I wanted to emphasize that was kind of the kickoff announcement from Hugh Brock is that we built a lot of this technology, or we built pieces together with Red Hat, including some that we created from scratch, all the infrastructure that could be integrated together for a university in a way universities need it, where you have PIs, requesting allocations, having students and associating them with institutions, and then so all the mechanisms that we need to make this available for academia, as well as we're OpenShift, OpenStack, OpenShift AI, and then ESI, which is again using a lot of those components, but working with Red Hat engineers and our own folks to actually get that part together. And what's amazing is Red Hat is now committed to us that they're going to be with us doing this in a way that's economical, which is huge, because till now it's been Hugh begging hat in hand for money, or not for money, for licenses, so we didn't know if this was economically viable from, next year or the year after. We sort of believed we had a very strong partnership and that everything would be fine, but it's hard to convince, I don't know if, none of us have had any experience in academia of using products from companies and then them quadrupling the price or giving us from zero to a very large price a year later, right? So I think that there was concern about that, and just, it's not that I didn't trust Red Hat, but having that as a commitment from Red Hat is massive, and further the fact that it's just for NERC, it's just for us, which what it means is that there's this incentive if other universities see what we're doing, that everybody will join us. Like, we want this to be a partnership. We want this to be open to universities joining us, because if creating a critical mass, and I think we now have this incredible incentive. So first of all, like, thank you, Hugh. This is incredible. I guess that, so there's AI, the marriage of data and compute. This is, we sort of had a series of things talked about there that really excite me. Till now, we've replicated a bunch of what I think are the core capabilities that people need, and I think we're useful. I think that there's incredible opportunity to do something that no cloud does today, by actually having deeper understanding of the relationship between things, the association, that marriage between data and compute. And it's not just a pipe in, it's not just a high-level idea, it's actually realizable. I mean, the things that Uli's been talking about, the things that Mark was talking about, who just left, I guess, and how Larry introduced that. This, to me, is where I think systems researchers, we have this opportunity to think about of doing totally unique and novel things. It took a lot of work to get to the point where we're reproducing what the public cloud does. Admittedly, not perfectly, but we have core capabilities that are useful. But now what I'm really excited about is having, every time people use these services, them improving in some fashion through the cooperative caching, through the understanding of workflows and integrating that to scheduling, through the memoization. These are incredibly powerful notions, and we all know these things go on in cloud services in the public cloud, but they're done, in a sense, improving their service, and who knows how that's actually monetized. Here, I mean, we should be explicit about this. This is what we're doing. You come to our cloud, you're contributing your usage to improving our service, to get more science done on a common platform. So, I'm sort of thrilled about what's come together. We've got the core components, and thank you, everybody, that participating. I think that every year till now, part of this has been about selling the potential. Of course, it's still that to some extent, but I think it's gone beyond that. It's like this, I think you've given us lots of food for thought on where we go. I mean, the notion of a data commons, to me, is really profound, figuring out how we actually move forward on that. What are other things that people want us to take back as feedback from this event? Okay. Tara says you all want to go home and I should shut up. That what? I don't think so. The question is, has anybody told us we need GPUs? All right. Thank you, everybody. I really appreciate this.
Yeah, very quickly, I just want to do a quick thank you. I know, Michael, thank you yesterday. A fine thank you to all the people that work on the NERC and have made all of this possible. And I just want to be a little bit more specific as far as the workshop. I want to thank, first of all of you for coming and making it a dynamic, educational, learning, growing experience, because I really think everybody got an awful lot out of these days, and it wouldn't have been possible without all of your participation. I want to bring a call out to Stephen and Jen at the front desk, our students, Brendan and Amaya, who've been helpful. I want to thank our caterers who've kept us all fed for breakfast break, lunch break. And I want to thank Ken, who's been up in the room with the Let's folks, making sure everything happens. And I really want to thank the Let's folks. I want to thank, that's our audiovisual group. We call them Let's here at BU. Whoever knew you'd have an audiovisual emergency? And they sure did take care of us really well. And thank you very much. That's Mike and Simona and Bo, so thank them very much. And I could not possibly Star of the day, star of the week, star of the semester, star of this, Tara Moran. Thank her. None of this would happen without her. So I thank all of you. I thank Tara tremendously. This has been a wonderful experience for all of us, and see you in 25. Thank you very much.